Good morning. We'll start in a couple of minutes, but if someone online could confirm that they can hear me, that would be great.
I can hear you.
Okay, thank you.
Yeah, same.
Excellent. Okay, let's get started. I'll share my screen. Okay. So a few practical things to start with. Let me try to get the chat a bit better in view. Okay. Right. So welcome to this training, organized by the Flemish Supercomputer Center in collaboration with EuroC Belgium. So this is a link to the repository for this training, but I'll just put that in the chat because that's a lot more convenient. There you go. And that will bring you to this page here, which is a brief description of what this training is about, but which also has a link to the corresponding GitHub repository. And in the GitHub repository, you will find the presentation I'm using, which is here, but also source code examples, which are here and which you can look at afterwards if you like. Also, feel free to clone the repository, fork the repository, whatever. You're very welcome to do that. Okay. It's also a good idea to follow us on LinkedIn. Then you get information about upcoming trainings, but also other news related to high-performance computing, mostly in Flanders, but also of interest to some other parts of the world. Okay, so throughout the slides, I have a number of typographical conventions just to try and be consistent and let's say make things either visually appealing or a bit more easy to follow. So one of those is that inline code file names and things like that are set in a monospaced font. I just realized that I don't have my pointer. So let me get over for a second. Okay, that makes life a little bit easier. So basically, as I said, a monospaced font, such as here, for instance, this part. Okay, why don't I get the marker? Yeah, and I don't need this clicker either, but okay, well, let's not go there. So longer code fragments are typically in on a grayish background, same font, and if applicable. I don't quite remember whether there are any in this presentation, but if there is a data file, it's on a differently colored background in order to clearly make the distinction between that. So from time to time, you will see this ellipsis here. So that basically means not enough screen real estate to put the information here. So that means that either it is on a previous slide already explained, or it will be explained on the next slide, or it's fairly obvious. Like for this data file, for instance, it just means more of the same. But at any rate, all the code which has been used in order to create these slides is available in that GitHub repository. So you can always check there if you want to. Terminal output is rendered in on a black background, so to show you, well, okay, this was produced by output. I also use this icon quite a bit. Something that is good practice is highlighted that way. If something is bad practice, well, okay, you get the drift. So that's basically easy. Also, it would be nice if this is interactive, so feel free to type questions in the chat. Also, we are not that many, so you can just activate your microphone if you have a question and you think, okay, this is not really something that is easy to type in the chat, then feel free. The more interactive this is, the nicer it is for me, and I hope that it is also more useful for you. Okay. That being said, what is Julia? Why would you actually want to know about it? Would you actually want to use it in new projects? So that's essentially what this training is about. It will guide you a little bit on what Julia is, what its features are, and then of course things get opinionated, what I like about Julia, what I dislike or think that are not necessarily the best design decisions. So basically I'll mention all that, and I'll try to contrast that with languages you know, like for instance MATLAB, but also Python and Fortran, C, C++, and so on. Okay, so that sets the scope a little bit. Again, many of the things many of my comments on features are of course personal and are of course opinionated. So take them at face value, make up your own mind. That is what this training is about, to give you an idea of, at the end of the day, you would like to start using Julia or not. Okay, so the first thing when you read anything at all about Julia is that it is clearly influenced by MATLAB. And indeed, it tries to cover, let's say, the same domains, programming domains, as MATLAB tries to do. So scientific computing. That's already a nice thing, because it's a language that from the ground up is designed to do scientific computing. So that's rather nice. In that respect, it resembles MATLAB. It also resembles Fortran in that respect. So that's actually good. So if you look at the mathematical notation that Julia allows, then I'd say it's a little bit half-baked when I compare that to Mathematica, which actually goes the full way. So I'm a little bit skeptical about that, but as you will see what I mean by that. But basically, it's an attempt, not necessarily the best I've ever seen. So what is also quite interesting is that it is not an object-oriented language. So as opposed to C++ or Python, which are very much object-oriented, Julia is not. Okay. So of course, object orientation has been invented in order to deal with certain software development challenges. So the question is, of course, how Julia tackles these same challenges, because obviously they don't change if you move from one programming language to another. So basically that means that whatever you need or want object orientation for in other programming languages, Julia must somehow offer an alternative. And it does. We'll see what it is and how it works. It does have a very nice typing system. So basically, that is an inherent part of Julia because it offers quite a lot of opportunities for optimizations by the compiler. So that is, of course, an interesting feature. And then it comes with a package system, so environments are built in as well. So that's also a feature which I like, because for most programming languages, you need something that is not in the core language. You might argue that pip more or less serves that purpose in conjunction with virtualenv for Python, but yeah, it doesn't really go the whole way. You could argue that things can be better. And then, of course, in the Python world, you have things like Mamba, Conda, etc., etc. Quite a number of ways to deal with your environments, UV and so on, more specifically to real Python development and so on. So if you were to compare that to the C++ world, you do have a number of package managers like Conan, like CPM, and so on. So basically, the nice thing about Julia is that it's actually built in. So there are many design decisions that are interesting in the sense that they are different from what you might expect, or not. That depends a little bit on where you're coming from. But at any rate, it's, from the design perspective, an interesting language. Okay, so how do you run Julia? Basically, you have a number of possibilities. So one of them is to simply run it as an interactive command line application. So basically, I could do that in the terminal. And then if I just type Julia, it's going to start that interpreter. Hopefully. Yeah. So here it is. And now I can start typing Julia statements. For instance, a very impressive one, which hopefully evaluates to 15, and it does. So basically, this is what you might be familiar with from, for instance, a Python interpreter, which you run interactively, or from MATLAB on the command line. So this is quite similar. It works quite well. So basically, sometimes it's useful to quickly try something and do that using this command line interface. Getting out of it, Control D is going to do that. Okay, let me. I notice that I have an environment active. That should not be the case. Okay. So that's one way to run Julia interactively in the shell. And then, of course, you can also run scripts. So like you would run a Python script. Of course, this is a Julia script. So basically, Julia followed by the file name. And it will actually run and do stuff. Also, you can use JupyterLab. Again, you start Julia interactively on the command line. And then you use using iJulia. Note the uppercase I and J, that's for interactive Julia. And when you run that the first time, that using statement, it is actually going to download the packages required. Well, iJulia basically, and its dependencies. So that will take a while. Of course, the second time those packages are installed, and they don't need to be downloaded anymore. And then again, the first time you do this, you would have to install a kernel. And again, that's done using the iJulia package, which you just loaded, with the install kernel option, and then the name of the kernel. So this would be for Julia 1.12.1. Okay, the latest version is in fact 1.12.5. So if you do this, just make sure that you pick the version which corresponds with your current Julia kernel, with your current Julia version, and then you can start JupyterLab. So maybe let's do that. I'm going to try to make sure that it ends up here. So let's again start Julia. Okay, so as you can see, it's Julia 1.12.5. Okay, so using iJulia. As you can see, the command line interpreter is intelligent. It will start suggesting things as you type. So in this case, I don't need to install the kernel. I already did that. So the only thing I need to do is to run JupyterLab. And note, that's just a function which you execute. So it's going to fill your screen with a lot of feedback, information, etc., etc. And then basically it should start the Julia kernel. Sorry, the Jupyter notebook. So here it is. And basically, one thing, I shouldn't have done this, but one thing that is different from what you're probably used to if you use JupyterLab directly, and you do that, for instance, as from Python perspective, then basically JupyterLab is going to start in the directory in which you actually start JupyterLab. So that's not the case for JupyterLab started from within the Julia interpreter. Basically, you start from your home directory. So, okay, it's a design decision which may or may not make sense, but I'm just pointing it out because basically that's what it is. As you can see, indeed, I've got a kernel here for Julia. The name is pretty stupid. I'd have to change that at some point because it's a little bit silly, but okay, never mind. And then, of course, you can go to a relevant directory. So in this case, that would be this directory, which is basically the one which is in the, well, which is the one which is in the repository. And then you can open an arbitrary notebook. Let me see, for instance, this guy here, Julia features. Okay, and then I can start evaluating that. So, for instance, this cell here, hopefully, again, evaluates to 4, and indeed it does, etc., etc. So, of course, all Jupyter features, JupyterLab features you're familiar with, are, of course, available in this interface as well. So, that should give you very little surprises. Okay. So basically, again, if you have the Jupyter kernel already installed, then you just do using iJulia, JupyterLab, and you're good to go, as you saw me doing, because yeah, I already had the kernel installed. So what I probably did here was actually not putting Julia here, something like that, when I installed the kernel. I'll have to redo it at some point in order to get it a little nicer. Okay, anyway. So that's very easy. So let's dive into the language. And of course, the first things which you do are basically expressions. So of course, there are variables, and you can assign two variables using the assignment operator. The assignment operator is simply the equality sign. So very few surprises, I guess. Then there are arithmetic operations. There are no surprises. Basically, addition, subtraction, multiplication, division. I'd say no surprise there. The power operator is basically the caret. So that's similar to MATLAB. That is different from Fortran and Python, which have the double asterisk as the power operator. Okay, then there is integer division, and that's interesting because it's actually it's actually a Unicode symbol which is used, and you get that interactively in Jupyter notebooks using /div followed by a tab. I'll show you in a minute. Now, that is not so very convenient in the terminal or in an arbitrary editor. So basically, you can also simply use the div function in order to do the division. So let me show you what I mean by the Unicode stuff in a notebook. I'm just going to open a new notebook, which is a bit more convenient. So basically, what I could do is tree div top. Nothing happens. Okay, second time it does happen. And now you see that completion is offered, and indeed it's this division symbol operator. Okay, so of course integer division should give me 0, as it does. Reverse div 3 should give me 1, and indeed it does. So there are quite a number of such operators available in Julia. We'll see that. Whether or not that's a brilliant move is open for interpretation. Okay. So comparison operators, again, not necessarily surprises. It depends a little bit on your background. So equality is double equality. That is similar to most programming languages, I'd say. So probably no surprise. The is different from is exclamation mark equality, or alternatively you can type \ne and tab, and then you get this is different from symbol, again a Unicode thing. Less than or equal, again for less than or equal you have a Unicode alternative, \le and tab, and similar for larger than and larger than or equal. Okay. Object identity, so basically are two things the same object, as opposed to do they have the same value? Do they have the same value is with the equality operator, so basically the double equal sign. Are two objects the same thing? That is the triple equality sign, or the triple equality operator. So this is something that you can compare to the is operator in Python. It's the same thing. It serves the same purpose. Then you've got logical operators, and again, people familiar with C++ will recognize this. So the not is the logical not is the exclamation mark, the logical and is the double ampersand, and the or, logical or, is the double pipe, basically. Okay. There's also function composition. So basically, you can do that with the with an operator, again a Unicode operator, circ rather, followed by tab, and that will compose several functions. So, for instance, I should be able to compose some cosine x, cosine something, let's say 1.3, and basically, okay, that's not working. That's a little bit weird. Okay, I'd have to check what's going on here. That's a little bit weird. Probably I need brackets. Yeah, so basically I need to put the brackets, otherwise it's not going to work. So basically that means first apply the cosine function to the argument, and then apply the sine to the result. So that's an operator which may or may not come in handy. Most programming languages don't have it. It's annoying that it uses the Unicode notation, so I'm not so sure that it's so very useful. What is useful though is the piping operator. So no exotic Unicode symbol for that. Basically just pipe followed by larger than. And we'll see an application of that later on. So the piping operator I do like, actually, and I'm very much looking forward to Python ever introducing it. I'd hope it does, but yeah, for now it isn't. So for those of you who are familiar with C++, indeed, if you have views in C++, you can indeed also use a pipe operator in order to chain those views so that you can nicely express, let's say, the flow of data as a pipeline rather than as nested function calls. Okay, so one of the things that Julia allows you to do is to leave out the multiplication operator when you are multiplying a constant and a variable. So for instance, what I can do, let me assign x the value type of 3. Okay, so I can type 2x, and that's the same as 2 times x. But on the other hand, if I have y equal to 2.1, I cannot type xy. It's going to complain. As you can see, parse error. It's unhappy. I cannot do this. So this is what I meant with my remark on the first slide, that unfortunately, yeah, sorry, there is a question about, yeah, the cosine. Yes, indeed. So basically, this would do the same thing. So sine, cosine, what was my 1.3? That would be the same thing. Exactly, yes. So that's basically why you can question whether this function chaining operator makes any sense or not, because yeah, it saves you a little bit of typing with respect to brackets. Whether it makes things more clear is debatable, and at the end of the day, it's more typing. So I don't know whether it's up to you, but I don't really see a nice application. Anyway. So basically, this is what I meant with a half-baked attempt at mathematical notation. So for me, this is not consistent. This only goes halfway. So yeah, okay. If you look at the Julia community, they seem to like it. So yeah, if you want to follow Julia idioms, you can do that. But yeah, again, I'm not really very impressed. Okay. So variables, of course, variables are the usual thing. They can actually also be Unicode. So for instance, I could have a variable alpha, and again, same thing. I start typing \alpha, and basically I can do that in 2 steps. So this, I can assign a value to that because it's just a variable like any other variable. And then I can do 2 times, what is it, alpha. And as you can see, that works nicely. Again, does that make sense? Up to you. Sometimes it's nice in notebooks because yeah, that makes you or brings you a little closer to mathematical notation. Is it worth the bother? I don't know. So variable names in general, of course, start with either a character or an underscore. They can consist of yeah, letters and digits, where letters can be Unicode. So for instance, I could also, if I were so inclined, define a variable alpha beta. Okay, so basically now I have a variable alpha beta. So a letter in this context is basically a Unicode letter in whatever or a script that you are familiar with. So basically it should be possible to use Greek letters, of course, but probably, just let me try because now I'm curious. Can I use Hebrew letters? Let's see. Oh yes. So basically, I can use Hebrew letters as well as I want, if I want. Okay, it's not really a surprise because it's just Unicode, but still, I never tried it, so it's nice to see that actually that is possible. And of course, other scripts are supported as well, as long as you know the Unicode name for it, you can use it. So if you have several words making up a variable name, just separate them by underscores, and by convention, variable names are lowercase, which brings me to the fact that, of course, Julia, well, not of course, but basically Julia is a language that makes a distinction between uppercase and lowercase. So it is case sensitive. So that means that Fortran and is MATLAB case sensitive? No, it's too long that I didn't use MATLAB. Anyway, Fortran is definitely not case sensitive. So if you come from there, remember this is a case sensitive language, as most languages nowadays. Okay, so function names, same thing. They are typically also lowercase, can contain Unicode. Again, underscore to separate words. And there is another convention which there is another programming language that does the same thing, but now I can't remember which one. Anyway, if a function modifies its arguments, you should append an exclamation mark to it. We will see examples of that. Basically, it's a convention, but you are really supposed to follow it, because that is a visual reminder that that is a function that actually modifies its arguments, as opposed to mathematical functions that don't do that. Okay, the last thing that gets names in Julia are types, and again, they can be Unicode and so on, but those are typically camel case. So essentially, they start with a capital character, capital letter, and words are indicated by capital letters. So to give you an example, my type would be appropriately capitalized. Okay, so this is pure convention. Everything else works. Only, of course, if you start using a programming language, it's a good idea to, let's say, try to stick to the conventions used in the community. And this is one of those conventions. So I would suggest you stick to it, but it's up to you. Okay, so one of the things that the Julia community also says, well, okay, Unicode names are cool, but don't use them in user-facing APIs. So basically, if you write a library of Julia functions, make sure that the function names in such a library do not contain Unicode characters. Why? Well, it's easy to get them typed in Jupyter Notebooks. That's very easy. / something followed by a tab, and you're good to go. But typing those Unicode characters in an editor, like for instance in Vim or in VS Code or anything like that, is going to be a lot more annoying. So if you create a library and users really have to fish into the documentation in order to find out how in their editor they can get Unicode characters typed, they are going to be unhappy. So typically don't do it. My personal rule of thumb is I use Unicode characters in notebooks, if it makes sense, for instance, because of the mathematics which is involved, but never ever in Julia files or in Julia modules. Okay, that being said, yeah, as usual, follow the conventions of the community. That would be good practice. Okay, so we've discussed variables, we've discussed expressions. So the next thing, of course, is functions. And you see something that might surprise you. You see functions and methods. But before we delve in, maybe one thing more about Unicode stuff. By the way, for the Python people, you can do the exact same thing in a Jupyter Notebook. So you can also have variables that have Unicode names. Not everyone knows this, but that is actually the case. And if you really want to torture yourself, actually C++ also supports naming names that contain Unicode. But yeah, really don't go there ever, because that's really annoying. Okay, so functions and methods. Basically, function definitions will remind you of how MATLAB does things. So they start with the keyword function. The body of the function ends with the keyword end. Okay, so the body of the function runs throughout this, this code fragment, of course. So the name of the function is linear scale, and it takes three parameters, x, a, and b. Okay, just for the sake of the argument, it's introducing a local variable term, which is just a product of a and x. This is totally useless, but okay. And then it returns term plus b. Okay, so very, very, very useful function, but it's just to illustrate what a function definition looks like. Okay, that's one option. The other option is that you leave out return. You don't have to have the return. The semantics is that a function is either going to return whatever is in the return, or whatever the last statement is that's executed in your function. So in this case, the last statement would be term plus b. So whatever that evaluates to is going to be the return value of the function. Okay. Yeah. Indeed, notation is very much inspired by mathematics, and indeed a little bit of Mathematica as well. As I mentioned, they don't go all the way. In Mathematica, you can write something like x space y, and that will be interpreted as a multiplication. In Julia, you cannot do that. The syntax does not allow that. So yeah, it's inspired by and taken halfway. So that's, yeah, a bit my take on that. Okay, so in general, but again, that's an opinion. I like return because I make it very clear also to myself that that is going to be the function value. So whether you use return or not is essentially up to you. The notation without it is very MATLAB-like. You would do the same in MATLAB. Okay, so basically that is quite straightforward. A very simple function like this can also be written with a different, or defined with a different syntax. So I just specify the name of the function, the parameters, and I assign an expression which is the result of that function. Okay, so that is also a way to define functions, and of course for short functions that makes quite a lot of sense. Just like many other programming languages like Python and like C++, lambda functions are supported. So basically the notation again is like this. So basically you state the parameters of the function, and then you use an arrow and the expression which is returned by that function. Okay, so many ways to define functions, essentially up to you what you prefer. Okay, so arguments can be optional. For instance, this is a function that compares two numbers, real numbers, and of course equality between real numbers is not really a good idea. So basically it's up to rounding error, etc., etc. So essentially you want to check, in this case, whether you have an absolute error which is less than a given delta. And basically by specifying the function signature like this, so with delta default value 1 to the power 10 minus 5, basically you specify a default value. So I can use that delta argument or not. So basically I can call the function almost equal with two parameters, two arguments, a and b, or with three, where then the third is bound to delta. So in this case, in the first invocation, the first call of the function, delta is going to have the default value 10 to the power minus 5 in the second call, where I specify the value of delta. It's of course this value of delta that is going to be used. Okay, so this is again very similar to C++, very similar to Python, and also very similar, by the way, to Fortran. Well, not so similar to Fortran actually. Okay, so if you have keyword arguments, so basically something like kvargs, key value arguments in Python, what you do is you separate the positional arguments from the keyword arguments by a semicolon. So basically, x and y are positional arguments, epsilon and abs are keyword arguments. So basically, I can call that function without any arguments. Well, okay, without any keyword arguments. So basically, just with the positional arguments a and b. In that case, the default values for epsilon and for absolute are the ones which are specified here. Or I can specify one of them or both using abs equals whatever or EPS equals whatever. So basically, similar to Python, only don't forget that if you have keywords arguments, you have to separate them from the positional arguments with a semicolon. That's actually the only thing to remember. Okay, you might have noticed something that, depending on your background, thought, well, that's a bit weird, because I said, okay, well, the section title here is essentially functions and methods. And typically, if you come from an object-oriented programming background, like for instance C and C++, typically functions that are defined on objects that belong to classes are typically called methods. So for me, methods is immediately associates with object-oriented programming. And one of the things I mentioned in the first slide is that if Julia is many things, it's not an object-oriented language. So why then methods? Well, methods in Julia actually has quite a different meaning. So basically, it is a specific overload for a function. So basically, just like in C++, you can overload functions, which means the functions have the same name, but they have different parameter types. So they have a different signature. And basically, these overloads are in fact called methods in Julia speak. So basically, we have an example here. It's a very silly function. So basically, it just prints that the argument is an integer. So let's take that apart. It's a function definition. So we have the function keyword, no surprise. We have the end, no surprise. The function name is show type. And then we have the parameters. So the new thing is that in this case, the type of x is specified. And the notation may seem a little bit weird, but basically the double column followed by a type is actually indicating that x should be of type integer. Okay, don't worry, we'll talk about integers and types more generally in a minute in more detail, but you see where this is going. X is supposed to be an integer, and basically the value of x is being printed, and okay, it says it's an integer value. Okay. Then we have a second function, the exact same name, but different signature, because the parameter type is different. So basically, in this case, x is a real. And again, almost the same thing happens, only the message which is printed is slightly different. Okay, so now we have a function show type, and we have two methods. One for an integer parameter, the other for an real parameter. Okay. So if I do show type 5, 5 is going to be an integer. So 5 is an integer value. If I call show 5 on 5.0, that's a real value, and indeed we get this prompt. So basically, this is called multiple dispatch. So depending on the types of the arguments of a function, the correct method is actually called. And that's done by the compiler based on type information that it has. Okay, so one of the things you might think when you come from a background of C++ is, okay, why don't I just put types everywhere? Because basically in that case, I give the compiler more information and the compiler will perhaps do a better job. Okay, let me first step back for a second, because it's one of the things that I did not mention explicitly, but I've mentioned it implicitly a couple of times, compiling. So what's actually going to happen under the hood with Julia, and that makes it quite different from a number of other programming languages. So what's actually going to happen is that your code is analyzed, and it's going to be compiled by the Julia compiler to machine code before it's executed. Okay, that's cool, but that has a number of consequences. So that means that the first time a function or method is called, that function or method will first have to be compiled. So that takes a while, because the code needs to be analyzed, the compiler needs to translate that into an intermediate representation, it needs to be optimized, then the compiler needs to generate appropriate machine code, etc., etc. Okay, so the first invocation of a function is pretty slow. Okay, it's rather fast, but compared to what it can be, it's pretty slow. But of course, subsequent invocations are going to be very fast, because the code has been translated into machine instructions, which run very, very fast, provided the compiler does a good job and does appropriate optimization. Okay, so you might say, well, okay, given that there is a compiler and compilers typically need information, if I provide information about the types all the time, the compiler will do the best possible job. Well, no, that's not the case for several reasons. First, the compiler is pretty smart, so even without type information, it's going to do the right thing in many situations. That's one thing. The other thing is that although you start out by writing a function for a given type, that code might actually work on a different type as well. So basically, in that case, the compiler is automatically going to detect, well, okay, given this type as input for this function, as parameter to this function, I can actually recompile for different types and get better performance. However, if you specify the type explicitly, then the only thing the compiler can do is convert the argument to the type that the function expects and run the compiled code. And that might be worse than actually letting it compile for the new type you're specifying as an argument type. So there are dragons here. So essentially, the rule of thumb is just use type annotations when you need them in order to do multiple dispatch. So basically, that's a little bit the approach that is suggested. And that should give you actually better performance. Okay. So you can also have a variable number of arguments so a variadic function in C, C++ terminology, or what's it called in Python? Basically, yeah, when you have a tuple, I can't remember, KV args and the other, and args, I think. Okay, anyway, so this function here, as you can see, the idea is actually that what I want is I want to check a point x and a certain interval around it, delta, specified by delta, and all the values which are arguments of the function should be close to x in the sense that the difference of the absolute value should be less than delta. Note that here I actually used, again, Unicode for a variable, as I already mentioned. Yeah, in this case, it's pretty innocent because it's not a keyword argument, but don't use Unicode in keyword argument names because that's user facing. Okay, so I expect 0 or more values essentially, and that's indicated by appending an ellipsis, so actually just 3 dots, these are 3 separate dots, to the name that will hold these values. Okay, so that is values in the function body is going to be a tuple. Okay, you are familiar with tuples from Python and from C++. So essentially, in terms of Fortran, you can see them as a user-defined type. So basically, it's the same thing. Okay, so one of the things you can do is iterate over values in a tuple, just like you can iterate over a list, iterate over an array, and so on. Okay, so let's take this expression apart here. So we have a number of things. We have the invocation of the mop function. Okay, so the mop function is going to apply a function to something that you can iterate over. Okay, so the first argument is always a function. The second argument is something you can iterate over, in this case a tuple. Okay, the function itself, as you can see, is a lambda function. It takes a single parameter y, and it is going to compute true or false, depending on whether the absolute value of x minus y is less than delta. Okay, note that this lambda function can use any variable which is in scope. So if you compare that to C++ lambdas, this of course would not work, because I would have to indicate that I want to capture x and delta by value or by reference, depending on whatever. So capture in Julia doesn't, you need not specify. It will capture anything that is in the that is in scope for that particular lambda function definition. Okay, so this function is going to be applied to every value in values, and the result is of course going to be an iteration of Boolean values, depending on whatever the value of values was. Okay, to that iteration, or to that iterable, we apply the all function. Okay, so the all function, the semantics is pretty straightforward. You have it in Fortran, you have it in Python, you have it in the STL of C++. Basically, it is going to return true if all values in the iterable are true. Otherwise, it's going to be false. And of course, it's lazy, because it will return or stop evaluating values as soon as it reaches the first false, because then it knows that whatever comes after is no longer relevant. Okay, so we can call this, for instance, this rclose with 0 as x, 10 to the minus 5 as delta, and then with two real values, 1.23 to the power 10 times 10 to the power minus 7, and minus etc. to the power minus 8. So this means that in this invocation, the tuple values will have two values, these two which are specified here. Okay. I could do the same with just a single parameter. So now values is going to be a one tuple, a tuple with a single argument. Okay, so it's pretty straightforward, and it's quite reminiscent of what you would do in Python. So yeah, it's a syntactic feature which personally I like. The notation is reasonable. It is reminiscent of what you would do with variadic templates in C++. So that's likely where the inspiration for this particular syntax comes from. I don't know. I wasn't on the language specification design team, so I have no idea. Okay, so that's most of what you need to know about functions. So of course the other thing, which is always useful to know with a programming language, is control flow. So basically, which statements have you got? How do you do conditionals? So here's an example of an if statement. As opposed to Python, you don't need to have a semicolon here after the if. As opposed to C++ or Fortran, you don't need brackets around the Boolean condition. So basically, it resembles MATLAB again quite a bit. So an if statement is always ended by end keyword, and then you can have optionally have an else. And if you need to chain several conditions, if, else if, etc., note that it is else if, it's one word. So that resembles Python's elif a little bit. Yeah, whether you like that or not is a matter of taste. I still prefer C++, else space if. Why introduce another keyword? I mean, just get your syntax definition right and you don't need all this extra keywords. But okay, it's what it is. So basically, else if in Julia land. Okay. This also introduces something that we will come back to later, but let me explain now. So there is a function error that takes a string as an argument, and of course you can guess what it's going to do. It is going to terminate the execution of your Julia code, and it will write that message on the screen when that happens. So if I were to call the function fact with a negative value, strictly negative value, then my program would stop and it would print that fact actually should be positive. Okay. You also notice that this is in fact a recursive function. So Julia has absolutely no problems with recursive functions, as opposed to, for instance, Fortran, where you have to declare a function explicitly recursive. So in that respect, Julia resembles Python, resembles C++, and so on, where yeah, recursion is just a normal thing. Okay, so nothing spectacular here. What you sometimes see, and of course this is not unique to Julia, you can do something similar in Python as well. Sometimes it's even done in Python, not that often is my impression, but okay. Where you see this quite a lot is in Bash. So what you can do is use the logical operators. Remember, we had a double ampersand for logical AND, double pipe for logical OR. So what we are using here is the fact that these operators short circuit. Okay, what do I mean by that? Well, depending on the programming language, there are two options. Either it is defined in which order the operands are evaluated, or it's left to the compiler or the interpreter. Okay, so both have advantages and disadvantages. An advantage of guaranteeing that the left operand is evaluated first is that you potentially don't need to evaluate the right-hand operator. So basically, for instance, if n is positive, then of course the left-hand operand evaluates to true. Okay, so that means, given that it is a logical OR, that the whole expression is going to evaluate to true anyway. So the Julia interpreter / compiler is not, at runtime, the error function is not going to be called if n is positive. Okay. On the other hand, if n is strictly negative, then of course the left-hand operand of this expression here is going to be false, but still it's possible that this expression evaluates to true if the right-hand operand evaluates to true. So that is evaluated as well. So basically this means if n is positive, just continue with the next statement. If n is negative, then error is evaluated and the execution is terminated with this error message. Okay. So very similar for the second line. So we check whether n is less than or equal to 1. Okay. If that is the case, the logical AND still has to evaluate its right-hand operand, because although the left-hand operand is true, the logical AND may be true or false depending on the value of the right-hand operand. So if n is less than or equal to 1, then the right-hand operand has to be evaluated, and that's return 1. So in that case, for n is equal to 0 or n is equal to 1, the function is going to return 1. Okay. Now, suppose that n is strictly larger than 1. Then, of course, the left-hand operand of the logical AND evaluates to false. So its right-hand operand need not be evaluated, because the whole expression is going to be false anyway, given that its left-hand operand is false. And so we proceed to the next statement, which is just a recursive call to factorial. Okay. So these two functions do the exact same thing in all circumstances for all given arguments. So it's a matter of style. Which one you prefer depends pretty strongly on your background, and of course you can mix and match. If you say, well, okay, in certain circumstances this feels more natural, then feel free to do it that way. If you say, well, okay, no, this looks ugly, I prefer this approach, again, feel free. Where, in my opinion, it might make sense is this type of construction. So basically, where you say, okay, I've got a Boolean condition. If that Boolean condition is not met, I have an error condition. So for me, this line makes a lot of sense, because otherwise you, especially if you have many of those lines, otherwise you get a lot of nested, well, not nested, but chained ifs, else, etc., else if, etc., etc. So basically that's a little overwhelming, and then this might be more clear, this notation. For this part, I'm not so very happy. But yeah, again, it's a matter of taste. You can do both. You can also do the same thing in Python, by the way, and typically in Bash, you can also do things like that. And also in C++. Don't ever attempt this in Fortran, because the Fortran specification says that you have no clue which of the operands is going to be evaluated first. So in Fortran, you can't rely on shortcut short circuit logical operators. Okay. Then, of course, the other thing which you want besides conditional execution is, of course, repeated evaluation, so basically loops. And there are a couple of types. So, of course, the while loop. So this loop is going to be executed as long as the Boolean condition holds true. And again, while end. So each statement in Julia is ended by the end keyword. Okay. Apart from that, not many surprises, I think. This function would just compute the greatest common divisor of A and B using this algorithm. Don't quite remember who it's due to. One of the Greeks. I don't quite recall who it was. But anyway. Okay. So very unsurprising, you have break, you have continue, just as you have in Python, just as you have in C++. For Fortran, that would be exit rather than break, and cycle rather than continue. Okay, but they have the exact same semantics. So if in a loop you hit the break statement, the loop terminates. If you hit the continue statement in a loop, the next, this iteration stops and the next iteration starts. So yeah, really no surprises. Okay, you also have for loops, and basically this is very similar to what you would have in MATLAB, to what you would have more or less. Oh, I need to plug in my laptop. Okay. So it's very similar to what you would have in those languages. Basically, I is the iteration variable, and it is in the range 2 to n. So depending on the value of n, I is going to get values from 2 to and including n. So for instance, if n is 5, the first iteration I would have the value 2, the second it would have the value 3, the third it would have the value 4, and the fifth and last would have the value 5. So like many programming languages, like Fortran, MATLAB, and so on, this is inclusive. So the n, I will have the value of n as in the last iteration. I'm stressing this because, of course, if you're used to Python, then basically if you use range here, this would be equivalent to range 2, comma. And in Python, if you want to include the n, you'd have to say range 2, comma, n plus 1. So I'm stressing the difference because that's false friend for Python programmers, of course. Okay, apart from that, I would say not that many surprises. So typically a range in Julia is specified with start, end, and step in the middle. So inspiration taken from MATLAB, of course. Okay, you can leave out a step if you want to. Then, of course, it's just by default a step of 1. Okay. So the for loop is also going to work on iterables. Basically, I could have done something like in my rclose function, I could have done for value in values, because value is a tuple and hence an iterable. That would also work. So that is very similar to loops in Python in general, and the range in C++. Okay. So a little bit about error handling. We already noticed the error function. So basically, this is going to hold execution, printing this string on the command line, on the terminal. You also have exceptions. A number of built-in exceptions, for instance, argument error, domain error, and of course, if you need to, you can define your own. Okay, how does it work? Well, basically you throw an exception, and in this case that would be a domain error. Okay, n would be the value, and then this would be the error message essentially, or the exception message. This will be constructed. Okay. So one thing to note is that throw is a function, and that is really weird from my perspective, because in general, in those programming languages I'm familiar with that have exception handling, throw is actually a keyword. That would be the case in C++, raise in Python. Those are language keywords. So Julia, for, to me, with mysterious reasons, does this differently. It implements that as a function. Okay, whatever. They probably have good reasons to do so, only I never bothered to figure out why that is the case. Okay, there is an explicit rethrow function, which is a bit weird because typically if you want to re-raise something in Python, yeah, you just raise and you're done. If you rethrow something in C++, you just throw and you're done. So, okay, it's there. So rethrow rather than throw something again. So that means, of course, there's also the usual try-catch construct or statement. So everything between try and catch is executed. If one of these things throws an exception, then that exception is called. And of course, in this case, I just catch any possible error. I might want to differentiate. So of course, I can do that. Notice there is again an end. This is a statement, so basically all statements, multi-line statements end with end. Okay, so in this case, of course, an error would be thrown, an exception would be thrown, and then basically, as you can see, I can get the value. So that would actually be the n here. That would be the value which is printed here. Okay. Maybe a little aside, because I'm not 100% sure that I have slides on it, so just mentioning it. Basically, yeah, I do, but not on this. So let me just explain briefly here. So print line is going to print something to standard output, and it's automatically going to add a line ending. Okay. So strings, as you can see, are delimited by double quotes. We'll go into more details later. But what happens here is this, or what is interesting here is this dollar brackets and then error.value. So basically, this is very, very similar to strings in Python, where you can actually embed variables and even expressions. So we already saw an example earlier where we had $n or $x for the value of x or n in that context. So basically in this case, it's not about the value of a variable, but rather this is an expression. So this is a Julia expression, and it will be evaluated, and whatever it evaluates to is going to be printed. So we would get something like don't use, in this case -1. Okay. All right. So of course you can have multiple catch clauses, as many as you like, each catching a different exception type. And of course you can also have finally, which is basically used in order to clean up. So I don't think there are many surprises here, besides the fact possibly that you have throw and rethrow as functions rather than as statements about keywords in the language. It's weird. Again, no idea why, but yeah, it's what it is. Okay, so just a little translation. Try catch is familiar to C++ programmers. That would be try except in the Python context. Okay. Exceptions are not a thing in Fortran. So basically, error handling in Fortran doesn't use exceptions. There is a paper which sort of gives a way to simulate it, but it's fairly exotic. I would not suggest to go there. Anyway, then functional operations. There are quite a number of them, and of course they're, as usual, tied to iterators. So you can do reductions, of course, computing the sum of anything you can iterate over. You can compute the product of anything you can iterate over. You can reduce, etc., etc. So to give you an example, what you could do. Okay, let me remove this because it's a bit silly. Let me collapse this and increase the font size a bit. That might be more comfortable. Okay, so what I could do, for instance, is the sum of 1 to 5. Okay, and as you can see, and as you can expect, that is 15. And I can also do the product. And that, of course, gives me the factorial of 5. So basically 120, as again you would expect. So these are functions which you probably expect. They exist in many programming languages, basically. But I'm a bit surprised because I have product here. Let me see whether that works. Because otherwise, no. So that is a typo, which I need to fix. So this should be prod, not product. Okay, I'll take a note. I think it's product in Fortran, if memory serves. It's not something that I can remember, but so that would be slide 19. Prod. Okay, so you need to fix that. The map function we already saw. Basically apply a function to anything in an iterator, and that gives you an iterator over the resulting values. So this is the exact same thing as you have in Python. Even the same signature, in the sense that you supply a function, you supply an iterable, you get an iterable. That's it. So that would be a bit similar to a transform in STL. You also have filter. Again, similar to what you would expect. It's going to take a function that returns a Boolean. If and that function is going to be applied to any element of the iterable. If the filter, so the filter function evaluates to true, the function will be part of the result. Otherwise, it won't be. Again, no surprise. Again, both STL and C++ and Python have this. Zip. That is something that you're also familiar with from both contexts. So basically that means take two iterables and construct pairs. And there is a module transducers that allows you to do some more sophisticated stuff. And that is actually also where the pipe operator comes in, which is actually quite nice. So basically we apply map to a sequence, to an iterable from 1 to 10. Okay, so map is going to apply this lambda function, and I'm not entirely sure about the syntax, so let me check whether this works, because it might work, but it might also be that I need brackets around the argument. These are always nitty-gritty details, so let's see whether that works or not. X to power 2, and I want to go from 1 to 10. Okay. Yeah, so actually works. It's not a problem. So for a single argument, apparently I can leave out the brackets here. So what I was doubting was whether I had to do this or not, but I don't have to. So okay, that lightens the notation a little bit, So it's definitely good not to do that. Okay. So basically, what I could do is something like sum, and that would give me the sum of all the squares from numbers of 1 to 10. And basically, that would be 385. I hope you're willing to believe that. So the problem with this is that you have to read this inside out. So basically, I first have to look here. That's going to be a sequence of numbers between 1 and 10 inclusive. Okay. And what am I going to do? There is a map. Yeah, okay. So I'm going to apply this function here, which is squaring all these values. And okay, that gives me a sequence of the squares of 1 to 10. And then I'm going to sum them. And as you see, reading this is not rocket science, but it feels a bit unnatural. So what we can do is just say, well, okay, I'm going to do map x to x squared from 1 to 10, and I'm going to pipe that into sum. And that gives me the exact same result. The difference is that now I can just read from left to right rather than inside out. And I can even go a step further. I can say, okay, 1 to 10. This I'm going to pipe into map, which now takes just a single argument, which I'm going to pipe into sum. And again, hopefully, no, I don't. Probably have to collect this. No. Okay. This somehow ought to work, but doesn't seem to. No. Very unhappy. Okay, so no, forget this. This does not work. I thought I could do that, but apparently I cannot. Okay. Does not map uses threads. That's why you need transducer. So basically, this guy here, the transducers module, actually has versions of map that are multi-threaded. So there are different functions there which do multi-threading. So if you're interested in that, have a look at the transducers module. That's why it's mentioned. So good point. Okay. So I'd have to figure out the. I think I can do this, something like this, but apparently not in this way. It's unhappy with the map. But I see. Okay, I don't quite recall why this doesn't work. It's pretty clear why, but that should normally. Well, the error message is quite clear. That's not the point, but it's probably something to do with this notation. Okay, let's forget about it. I'll check that later. What I messed up. Anyway, I do like this pipe operator. So you also have it for views in C++. You unfortunately don't have it in Python. But in my opinion, it is something that is really nice, a very nice language feature. Okay, this might actually be a good point for a break, because now we start on data types, which is, well, going to take a while. So it might be a good idea to have a break here. So indeed, the problem is that with the map thing is that it actually takes 2 arguments, but that is indeed the point, that you can skip an argument. So you sort of use currying, and I thought it would use currying automatically, but apparently it doesn't. So I'd have to check this notation, which I'll do during the break because now I'm too curious to not to know how I mess up. Okay, so let's have a break till okay, for convenience, let's make that break till 10:40. Okay. Meanwhile, I'll do some administration and figure out whatever the deal is with this map thing. Okay, let's resume. Share my screen. Okay. Right, so you can actually get it to work, but then it gets ugly. So basically, you pipe the range 1 to 10 into a lambda function, where the first argument is then that sequence, and then you the body of the function is the map, etc., etc. But this really gets ugly. So basically, that's really not what you want essentially. Okay, the reason for that is indeed, yeah, as you would expect, map does take 2 arguments. I thought it would automatically fill in this argument, but it doesn't. It does use the first argument, if possible. So basically, that's why it works for sum, but not for map, because of course it expects, as a first argument, it expects a function. So basically, there are no 2 arguments, etc. So it can't work that way. It can work this way, but yeah. Okay, don't do that at home. It just looks ugly. Okay. That being said, let's turn our attention to data types. So data types are really central in Julia, and you already know why, because it strongly depends on multiple dispatch. So on a function having several methods, multiple methods, and that's all based on data types. So there are quite a number of basic data types, unsurprisingly, all integer types which you might know and love. One which is a bit uncommon is int 128. So that would be a 128-bit integer. That's really huge. Okay. So as you can see, the convention is followed in the sense that types are camel case. So basically, it's capital I int, etc., etc. So this is very similar to what you would have in NumPy, for instance, with 8-bit integers, 16-bit integers, 32-bit integers, and 64-bit integers, and very similar in C++, int 8 underscore t, etc., etc. And of course, for each integer variant, you have an unsigned integer variant as well. So for instance, int 8 would contain values between -128 and 127 inclusive. uint 8 would be 0 up to 255 inclusive. Int 32 would be -2 to the power 31 up to 2 to the power 31 minus 1. uint 32 would be 0 up to 2 to the power 32 minus 1, and similar for the other types. So yeah, I don't think there are many surprises here. Then there is a Boolean type. Note that Boolean type is 8-bit. That is the case in all programming languages I'm aware of, and that's just of course because the way you can address memory is by byte, so by 8 bits, not by individual bits. So it's 8 bytes. So all of these types, int 8, uint 128, etc., etc., but also bool, are in fact specializations of the integer type. So int 8, int 16, etc., etc., are concrete types. Integer is an abstract type, and it encompasses all the integer types plus the booleans. Okay, then there's also the notion of a rational number, so that's also a type. Name is rational, and of course you have to, it's a parameterized type. We go into the details later, but basically you would have to define what the type is of the numerator and the denominator, and that would be given by the int type. So you could have a rational, curly brackets, and then, for instance, int 32. So basically that would mean that both the numerator and the denominator of that rational number are of that integer type. Okay. Then there are floating point numbers. So basically 3 types, float 16, 32, and 64. Okay, so float 32 is single precision. So basically that gives you 7 significant digits, and it gives you a range between, well, basically a range to 2 to the power 38. The smallest number you can represent, which is non-zero, is 10 to the power minus 38. For float 64, that's double precision. So that's basically 15 significant digits. And powers up to 10 to the power 308. So has rational the same precision as float 16? No. A rational number is not a floating point number. So basically I can essentially have arbitrary precision in the sense that if I have the rational with numerator 1 and denominator 3, it's the exact rational value. So it's not going, unless you convert it to a floating point value, it's not going to be truncated. It is the mathematical rational number. Does that make things more or less clear? Of course, how precise things can be depends on the integer type you're using. If you use int 8, for instance, then of course your rationals are going to be very limited in what they can express. If you use int 128, you have quite a range of very weird values which you could potentially use. Okay, so single precision, double precision, float 32, float 64. So to compare, C++, Fortran have single precision, double precision. Python itself just has double precision. Okay, in of course NumPy you also have the same range. The float 16 is half precision, and basically at this point in time still it is added mostly in order to deal with GPUs, because CPUs typically don't deal well at this point with half precision. That might change in the future, but at the moment they're not good at handling that. And basically on a CPU, typical CPU, operations in float 16 are going to be slow. So they would have half precision, so basically 3, at most 4 digits of precision, and a range, yeah, that depends a little bit on whether this is really a float 16 or a brain float. I'm not quite sure what Julia uses. I would have to look it up. I don't remember. Okay. So all these 3 types, float 16, float 32, and float 64, are concrete types based on an abstract float type. Okay. All of these things, so all the integers, but also the rational and the abstract float, are real. So a real number can be integer, or it can be float 32, or it can be rational with some specified denominator. So as you can see, we get a tree of types, where at the moment, at the top, or the root, depending on your point of view, you've got real. Then you've got 3 leaves. One is abstract float, the other is rational, and the third is integer. Rational is a leaf node, but abstract float itself is again a node that has 3 leaves, 3 children, float 16, float 32, float 64. And integer has many children. I'm not going to enumerate them. You can read them from the screen. So basically you get a tree representing types, where all the leaves are concrete types and all the inner nodes are in fact abstract types. That's basically how that works. You've also got complex numbers, and you get complex F16, F32, and F64. So basically, complex F32, as you can guess, means that you've got single position real and imaginary part. Complex F64 means you have a double precision real and imaginary part. Okay, so all these three types are instances, concrete types of the abstract type complex, and the whole thing then gets another parent node, which is number. So a number can be complex, it can be integer, it can be abstract float, etc., rational, and so on. Okay, then character type. So this is a single character. So that's a little bit weird for people who come from a Python background, where typically you don't make a distinction between a string and a character. So in Julia, there is an explicit distinction. A character is one individual character. A string is basically a different data type. Okay, so the character type is 32-bit Unicode, which basically means that character data represented as characters is not necessarily stored efficiently. For instance, if you were to use character for storing DNA sequences, which typically only have full values and perhaps some annotation to indicate missing or uncertain data, you would use 4 bytes for each nucleotide, while actually that would much better be done with an 8-bit character, which you don't have. Okay. So no, complex and real are distinct types. So complex does not have real as a subtype, and real does not have complex as a subtype. They're both children, so they're siblings from number. So the hierarchy is, we have number, either it's real or it's complex. If it's real, it can be integer, rational, or abstract float. Complex, it can be complex F16, F32, or F64, and so on and so on. So that's basically the hierarchy. So no, a complex number and a float and a real they do not overlap. They're siblings in this tree. Okay. The entries of complex. So basically the imaginary part and the real part of a complex number are always floating point values. And they depend on which complex type you choose. So if you have complex F64, the real part and the imaginary part are always going to be represented as double precision values. So what could have been done, but what has not been done, is that just like rational, complex would have been a parameterized type, where you would have complex, and then the type specified it similarly to this. But this design decision was not taken. Again, don't ask me why, because in my opinion, it would make a lot of sense, and it's also what the standard template library of C++ does. I don't know why they decided to make atomic types rather than parameterized types. No idea. For me, it's weird, but okay. So what you cannot do, essentially, is have a complex number that would have integer, real, and imaginary part. So suppose you would want 1 plus 3i, you would have to do that as 1.0 plus I 3.0i, something like that. And I hope that kind of answers your question there. to always specify the data type? No. So basically, is it always a good idea to specify the data type of a variable? No, not necessarily. So typically, you'll see a number of cases where you explicitly type things, and besides that, I would not recommend it. So a mistake which is very often made by programmers who start using Julia is type everything. No, don't. Type only what you need to type and nothing more. Leave the compiler and basically the analyzer, which is part of the compiler, leave it room to do its thing, because otherwise you're going to suffocate it and restrict its options. So that's essentially the idea. Of course, if you want something to be an explicit type, we'll see that in a minute, then of course you should make sure it is. Okay, so literal values. Basically, if you just type any integer, it's going to be interpreted automatically as an int 64. So a long integer in terms of C++. Maybe just for the record, because I didn't mention it, an integer in Python is actually a weird thing in the sense that it doesn't have a fixed number of bits. It will grow depending on the value the variable has. So basically, Python can represent integers of any magnitude, as long as you have memory to represent it in your computer. It can be handled, it can be computed on. So that's not the case in almost any other programming language besides Mathematica. Basically, typically, types have a size, and that determines their range, and that's it. So if I want to make sure that an integer is in a different representation, then I'd call the, let's say, the type function, and this will make sure, for instance, here, that 3 is interpreted as an unsigned int 8. Okay. So you have to do that explicitly if you want specific integer formats. Okay. So 3/5 is going to be irrational, and it does the obvious thing. Given that 3 and 5 are in fact int 64, it's going to consider this rational int 64. Okay, probably not a big surprise, but of course the / operator, well, it's not, is this an operator? Yeah, no. So don't confuse it with what happens in Python, where it is the integer division operator for integers. Okay, floating point. If you just specify floating point number, then it's going to be a float 64, so a double precision. If you use the E notation, it's going to be float 64. If you want it to be a floating point value, you'd have to use this F. Okay, so the strange thing is, if you come from C or C++, you would normally, in this circumstance, just write 5.1F in C or C++ to indicate that this is a single precision floating point value. Okay, in Julia, again, for whatever obscure reason, F is just considered the power of 10, and basically the 0 says, okay, this is 5.1 times 10 to the power 0. Okay, why they made that design decision, heavens may know, but it is what it is. So basically, to indicate that you have a floating, well, double precision value or floating point value. If it's a floating point value, make sure that you specify it explicitly. Okay, you might say, why does that matter? Well, basically, you have to be a little bit careful because of why we use distinct types. let me perhaps just, because I'm not entirely sure what your background is, let me just quickly try to explain this. So let me go to the previous slide again. Why do all these types exist? So basically, if we have int 8 and we have int 64 and even int 128, why do we bother? Well, probably it's very clear why that's the case. Essentially, if I can represent my data as int 8, then of course I can store much more data in memory than I can I represent it as int 64. So to give you an example, if I use a uint8 to represent a color, basically an RGB value would be 3 times a number between 0 and 255, so that exactly fits into a uint8. So the color of a pixel would take up just 3 bytes. That's it. If I were to use, okay, and now I have a million pixels. Okay, so basically that would mean 3 megabyte. That's it. Okay. On the other hand, if I would represent those same colors as int64, okay, that's 8 bytes times 3. That's 24 bytes. So for my million pictures, I would have 24 megabyte rather than 3 megabyte. Okay. That makes quite a bit of difference with respect to what you can store in the working memory of your computer, on the one hand. Also with respect to file sizes, that also makes a big difference. And more importantly, most of your code is going to be memory bound. Basically, it is going to, as a bottleneck, have the amount of data that you can get from main memory, so from RAM, to the CPU and back again. And of course, given that my representation consumes much less memory if I use a small data type rather than a large data type, that means that I can get much more data values of a small data type in the same time than corresponding values in a large data type. So basically my effective memory bandwidth, which is a measure which interests me quite a lot in high performance computing, is going to be much larger, potentially twice as much, 8 times as much, whatever, depending on the data type I'm using. So that's the rationale for why we have all these different integer types here. Okay. Similar for float, but there is another thing. Of course, float 64 versus float 32, that's a factor of 2 in storage, also a factor of 2 in effective memory bandwidth. But there is another thing with floating point values, and in fact also with integers, but typically we care more about floating point values in this respect. There is also the fact that this code hopefully gets factorized. So if I'm operating on arrays, and for instance, I'm adding 2 arrays, or I'm multiplying 2 arrays, or any similar operation, then basically that does not it happen on individual values of those arrays, but rather on groups of values. And then it depends how large these groups are, depends on the type I'm using. So basically for modern hardware, we have at least 256 bits. So that is 4 floats, or 4 double precision, or 8 single precision. So basically that means that in one instruction, I can add 8 array elements if they're float 32, or 4 elements when they're in float 64. So essentially, if I can get away with lower precision, and I do array operations, then my code might be twice as fast. So that's another reason, besides the memory footprint on the one hand, and the bandwidth, the effective memory bandwidth on the other hand. And then, of course, there's a whole story about caches and so on, which I won't go into. But basically, the bottom line is, if you can choose between single precision and double precision floating point values, in the sense that the precision doesn't matter, then it's better to use single precision. Of course, you can be forced to use double precision because of precision. Okay, so that being said, let's return to this slide here, and why it's important that there is something like a floating point single precision constant. Well, basically, suppose that you have a single precision array, and you want to multiply each element in some expression by a floating point value. Okay. Suppose you naively write 5.1 times xi. Okay. X is single precision. However, 5.1 is double precision. So the compiler has no choice. It will convert the single precision value to double precision, do the multiplication in double precision, and then convert the result back to single precision. Okay, that's on the one hand extra conversion, and on the other hand, if you do that on an array, of course it means half your vector length. So that's accidental promotion of the one of the operands to the higher type. And in order to make sure that that doesn't happen, you would have to specify 5.1 F0. In that case, the compiler sees two operands which are both float 32. It's going to do the operation in float 32, no conversion. You get the factorization which you expect, and you are going to be happy. So that's something that in scientific computing unfortunately matters, and that can have an influence on performance. Okay, so complex, very similar. The thing is, as suffix for the imaginary part, you'd have to use im. So in Python that would be j. Okay, here the choice has been made to use the im for imaginary. And of course, similar, if you want a single precision complex value, then you would have to use this f exponent notation. Okay. Boolean is simply true and false, all lowercase, like in C++, and yeah, not like in Python. Characters, just like in C++, characters are always delimited by single quotes. So this is the character A, this is the character new line. Strings are always delimited by double quotes. So unlike in Python, you don't have a choice. Strings are always double quoted. In Python, you do what you want. In C++, again, you would have the exact same as in Julia. Single quotes for the character, double quotes for the string. Okay, not that many surprises. So if you want type conversion, if you need type conversion, just use type names as functions and you're done. So if I want to convert an integer to a float, no problem, I could use float 32 and then the integer as an argument, for instance, and then it will be converted into the floating point value. Okay. String substitution. So there is a slide on it. So basically, I have a variable n in scope, so I can use the value of that variable. That's just $ followed by the name of the variable, or I can use an expression. And in this case, I would get as a result 2 asterisk 3 equals 6. 2n. Remember, I don't need to write the asterisks in order to have the multiplication here. So basically, this is what I would get. So this is, again, very similar to f-strings in Python, only you don't have to use something like f-strings. All strings in Julia are f-strings in that respect. Okay. So in Python, you would have curly brackets around n, and you'd have curly brackets around 2n. So similar, but just a little bit different. Okay. More sophisticated data structures, tuples. We already encountered them with the values. You also have named tuples, just like in Python. You've got structures. Those are interesting. Sets, dictionaries, arrays of two types, vectors and matrices. And you also have n-dimensional arrays, by the way. So let's have a look at vectors, matrices, and arrays first. Okay. So just like in MATLAB, and unlike NumPy, for instance, there is a distinction between column vectors and row vectors, which essentially is a good thing. So for instance, I can define V1 as a vector with 3 elements or 3 components. So the notation is square brackets to define the vector, and then I enumerate the elements, but they're separated by a comma. Okay, this comma indicates that this is a column vector. Okay, the row vector would be very similar, but without the commas. So basically, you can view the comma as a sort of end of line if you want, and basically that makes it, that allows you to make the distinction between the column vector and the row vector. So this again is similar to MATLAB. Okay, what you essentially get is a 1 times 3 matrix, by the way. Okay, so this is essentially, if you want, horizontal concatenation. So for a matrix, you would have this notation. So this would work basically used on based on the white space and the line endings which you give. So an alternative to that would be would be the first row, semicolon, second row, and so on. Again, inspired by MATLAB. So these are equivalent. And that would be the semicolon is then vertical concatenation. So you concatenate the first row and the second row. The space is horizontal concatenation. So basically, you concatenate by just specifying the space. Okay, so that's a very easy way to define column vectors, row vectors, matrices. But you can have arbitrary n-dimensional arrays, essentially, just like NumPy arrays. So basically, you have the array type. You specify the type of the arguments. So this is a templated type, parameterized type. You specify the initial value. So in this case, it's undef, basically meaning don't initialize. I'll do that later. Well, me as a programmer do that later. And then the dimensions. So this would be a 3-dimensional vector with the first dimension 3, 5, and 7. So this would be a 3-dimensional thing. Okay. And that's a typo because this 8 here should actually be a 7. Okay, let's make a note of this. So this is 24 and 8 should be 7. Okay. All right. So there are many functions defined on arrays or for arrays and so on. And many have to do with construction. And if you're familiar with NumPy, then or MATLAB, then you will recognize quite a number of them. So zeros is going to give you an array that is initialized where each element is initialized to 0. Ones is going to give you an array where each element is initialized to 1, etc., etc. trues, false, fill. So basically I can get an array with an arbitrary value given to each element. A range, so basically that would resemble a range NumPy. Random, this would be the elements are chosen from a random distribution, uniform between 0 and 1. Rand n from a normal distribution, etc., etc. So here's an example. I would get a 2 by 3 two-dimensional array, so 2 rows, 3 columns, and all values would be 3.14. Given that 3.14 is interpreted as a float 64, that will be an array with float 64 elements. Okay. What you can also do is create an array out of an iterator. So range is going to be an iterator. In this case, we start at 0, we end at 1, and we want 5 elements. So in NumPy terms, this is not so much a range as rather a linspace, similar for MATLAB. So this would be equivalent to a linspace in those languages. And what I would get, of course, is 0, 0.25, 0.5, 0.57, and 1. So basically, that would be this thing. And it's collected into a column vector. So collect is going to let you do that. It turns an iterable in a vector. Okay. There are many properties. So basically, what you would do, for instance, in NumPy is, suppose I have an array A, then I would get the element type by using a.dtype. And that would give me the type of the elements. So, of course, Julia is not object-oriented, so we need a function to get that. And that's the L-type function. So basically, the L-type of A would be float 64, as you can see. Number of dimensions is going to give you the number of dimensions of that particular array. So, of course, for A, that's again equal to 2. Then there is also size, and that's very similar to, on the one hand, Fortran, and if memory serves, also MATLAB. So basically, what it's going to give you is the size as a tuple, but you can give an additional argument, 1, 2, depending on the number of dimensions, which is going to give you the dimension or the size in that dimension. So if I have a 2 by 3 array, size A1 is going to give me the number of rows, size A2 is going to give me the number of columns. And the length is just going to give me the total number of elements. So essentially, that would be the product of all the elements of this tuple. Okay. Then strides is also interesting. So strides of A is going to give me a tuple 1 and 2. Okay. So this is quite different from what you would have in Python with NumPy, because in actually most programming languages I'm familiar with, strides are typically expressed in bytes. Here it's just in the number of elements. So what does that mean? Well, basically, if I want to go from the first row, sorry, I have to check. If I want to go to the next element, to the next row, I just go 1 position downward. Okay. On the other hand, if I want to go to the next column, I have to go all the way down and here. So basically 2 positions, because this is a 2 by 3. So this tells us a number of things. The first thing to note is indeed it's not in bytes. That's unusual, but whatever. The second thing, and that's more important, arrays in Julia are stored in column-wise. Column-wise. So basically, do I have a slide on that? It would be very useful, but I don't. So basically, everything in memory is of course stored as a sequence of values. So the sequence of values that stores or represents A is actually 1.2, followed by 4.5, followed by 2.3, followed by 5.6, followed by 3.4, followed by 6.7. Okay, so that's column major. We store the first column, then the second column, then the third column. Okay, you could make a different decision. You could say, okay, I'm going to store row-wise. So in that case, the sequence would be 1.2, 2.3, 3.4, then 4.5, 5.6, 6.7. That would be row-wise. So the slides tell you actually that this is column-wise storage. So this is very similar to Fortran, very similar to MATLAB, very similar to R. I didn't make many comparisons with R, but also R stores arrays in that way. And this is of course interesting to know and useful to know because what you want is to try to access arrays as much as possible in the order, array elements, in the order in which they are stored. So basically that has implications for a nested for loop, whether you should first iterate over the rows and then over the columns, or vice versa. So in the representation that is column-wise, you should first iterate over the columns and then in the inner iteration over the rows, because then the fastest changing index is the inner loop. Okay, so you have to be a little bit careful. Mixed precision, yeah, I'll answer that question in a minute. So basically, okay, now let's thread. Okay, I lost my thread. So let me just answer the question. Can you do mixed precision calculations in Julia? Yes, you can. Basically, I could say, okay, I want to do part of my calculation in single precision, but I want to accumulate in double precision. Yes, you can do that. The compiler is going to do the right thing. So basically, I would have to make sure that execution is in the correct order, so that the conversion of types happens when it should happen. But yes, you can do that. If you mean mixed precision calculations in the sense of GPUs, then of course it's up to the GPU package which you're using, but that should also be possible, yes. I'm not sure whether I answered your question, but yeah, okay. So the setup precision arbitrary, well, basically the precision is essentially determined by two things. That is the type of the data and potential conversions, either explicit via functions or implicit because the compiler has to convert stuff. So in that respect, it is, unless you mean, wait, yeah, so basically, I think what you're referring to is that in Fortran, you can specify a compile flag, which says in which precision you actually want to compute. So basically, whether real should be interpreted as single precision or double precision. The answer to that is no. That's not something that you can do in Julia. I don't know whether that was the question, but if so, no. That doesn't work the same way. Okay. So array and matrix operations. array indexing, okay, it's one based. So similar to Fortran, to MATLAB, etc., etc. Yeah, so just remember, if you need to translate between algorithms, for instance, Python or C++, to Fortran to Julia, or vice versa, remember indexing changes from zero-based to one-based. That's one thing. And typically, storage changes from row major to column major. So that has an impact. Well, the first has an impact on correctness. If you don't get your index arithmetic right, you have bugs. Simple. The other problem with row major versus column major means that you may have a performance penalty. With respect to the arbitrary precision thing, Pedro, if you like, you can explain. Because I have interpreted what you asked, but I'm not sure whether my interpretation is correct. So if you like, you can activate your microphone and explain.
Hello? Hello?
Yeah, we can hear you. Well, I can hear you. Can you speak for us?
Yes, yes, because I remember in Fortran we have this precision, yes, the kind function where we can set the precision of the variable. But here I can see that there is only floating point 16 and 64, and I wanted to ask you if you know that somehow we can set the precision.
Yeah, now I get what you mean. So basically, indeed, in Fortran, you could say that the kind is actually something like 6 or something. You could do that in Fortran, but what would happen under the hood is that it gets mapped to either a single precision or a double precision anyway, or potentially to a quad precision if your compiler supports that and if you have a runtime that supports that. But basically, it's also going to be one of those types, regardless of what you do with kind. So what you can do is compute the precision. You can do that theoretically even at runtime, but that is always going to map to one of these types. Either single precision, double precision, or potentially quad precision.
Mm-hmm.
But quad precision is going to cost you performance-wise, so unless you have a very good reason to do that, don't. So here the conversions are actually sort of similar. So rather than using kind, what I would do is, for instance, float 32 of 5.1. And that is going to give me single precision. As you can see, there is the F0 here. So that is going to be a precision value. And vice versa, of course, I can do float 64. Or let's not do vice versa, let's do it on an integer. As you can see, yeah, okay, I need to specify, of course, float, whatever, let's say 64. And then basically it converts to a floating point value. So that's essentially how that would work.
Okay, yeah. Thank you.
All right. Okay. That being said, so indexing, be careful if you translate from one language to the other, because your indices have a different range. From 0 to the dimension length -1, or from 1 to the dimension length inclusive. Okay, you can do array slicing. So basically, I would have a slice here from 2 to 3 rows and from 2 to 3 columns. So this is, of course, again different from Python, where that would be non-inclusive. Here it is inclusive. So this is the second and the third row. This is the second and third column. Slicing does copy. It doesn't alias as it does in NumPy. So basically this is an explicit copy. Okay, that has advantages and disadvantages. You can like it or not, but basically that's what it is. The advantage is, of course, that this is less error prone. The disadvantage is that it has a potential performance impact. Okay, arithmetic operators are annoying in the sense that you can do an operation between a scalar and an array. So in NumPy terms, broadcasting. However, you would have to use the dot operator, so dot plus or dot minus or dot times whatever. So basically, don't forget this dot, or it's not going to work. So that's different from anything I know. And personally, I really don't see why they made this design decision. It's very bizarre. And similar for array to array, but element-wise. So essentially, let me perhaps show it. That would be more convenient. Suppose I have a vector, an x and it's a row vector, and I have a row vector okay. If I want to add them, I would expect this, which nowadays works. Oh, that is great. Okay, I'm majorly impressed. That didn't used to work. Well, apparently it does. Oh, cool. Okay, now I'm very curious. Did they change this as well? No, this does not. All right, so basically here I still do have to use plus, and then it works as expected. And also, if I switch the operands, it will do the same thing. So x dot, let's multiply this time by 3, whatever. So basically, you see that works nicely. Okay, so that's a good change. I have to note that there is now an alternative for that. Of course, if you do a matrix, an array-wise operation, an element-wise operation, the sizes must match. If they have a different number of elements, the compiler is going to tell you that you shouldn't do such things. And that is clear. Okay. Matrix multiplication is just the asterisk. And then, of course, the dimensions must match because you're doing a matrix multiplication. And similar for the power, so just the caret is the matrix power. And then, of course, your matrix has to be square. Okay, otherwise that doesn't make any sense. So this is nice because it's intuitive. This is now nice. It didn't used to be nice, but now it's nice. This is bloody annoying. Okay, then you also have element-wise functions, so you can compute the square root of each element, but notice there's a dot here. So you would, again, let me test because it might have changed as well, but I would guess not. So let me do the square root of x. Okay, so indeed the dimension mismatch. The square root function itself is not defined on x, so if I add a dot, then it's the element-wise function applied to x. So yeah, bloody annoying, but okay, it is what it is. Yeah, I think you're often going to make mistakes with scalar array operations and with element-wise operations. If you've not done Julia for a while, it's likely that you forgot this, and this is, in my opinion, just annoying. Okay, so there is a transpose function, and for the complex conjugate, just use the quote. That will work. So again, this is quite similar to MATLAB, except that in MATLAB you can do dot quote, and then you get the transpose even of a complex, so you don't get the conjugate, the complex conjugate. Okay. There is a linear algebra module, and that contains quite a lot of interesting stuff, such as the determinant of a matrix, the inverse of a matrix, eigenvalues, eigenvectors, all kinds of decompositions, matrix decompositions, such as single value decomposition, QR, etc., linear regression, and so on. So basically, this linear algebra module is quite useful. Okay, so here's an example using linear algebra, and then I can just use SVD, which gives me these arrays. This function is also not going to surprise you. So just like in MATLAB, just like in NumPy, SVD is going to return S as a one-dimensional array rather than a two-dimensional diagonal array. So if I want to multiply it, I have to make it diagonal. And that's just a diag_n function, which turns a one-dimensional vector into a two-dimensional diagonal matrix. Okay. Matrix tensorial multiplications. So yes. So basically, the multiplication operator is indeed going to do the right thing depending on dimensions. Yeah. Okay. So of course, arrays are our bread and butter in scientific computing, but of course we need to create our own data types as well, and that's where structures come in. So a structure is something that you can sort of compare to a data class, if you like, in Python, or a tuple in Python, sort of, or a user-defined type in Fortran, or simply a struct in C and C++, because it's the same terminology. So it's a statement, declaration statement. So struct end. Pixel is going to be the name of the struct. Note capital P because this is a type. It's a type name, so it should start with a capital letter. And then we have several members of this structure. Basically, X, Y, and color. And I explicitly define the types here. So X is going to be a uint32, as is Y, as is, and color is a string. Why do I have to do that? Well, basically, this is a concrete type. So the compiler needs to know how much memory such a thing of type pixel will take. So it needs information about what X, Y, and color are going to be, so that it can reserve, when you create a new pixel, enough space to store something like that. So this is one of the occasions where you cannot skip typing. So here it's required. That's a place where you definitely do this. And then you can create a new pixel by specifying the values of these members. So X would be 3, Y would be 7, and the color would be the string blue. So this constructs a new pixel, and it's going to assign it to the variable P. Okay. Then I can access the members of a struct variable simply by using the name of that member. So this would print the string blue. I could think that I could set the color, and that's a bit of a surprise, because by default, a struct is not mutable. So basically, once created, it cannot be changed. that may or may not be what I want. So if I do want to change after construction the values of x, y, or color, I have to declare my type as a mutable struct. So the keyword mutable indicates that after creation, I can still change x, y, and color. So basically, again, I create a new pixel. In this case, it's a mutable struct. So this would work as before. And this assignment is now going to work because P is mutable. So I can actually change its value. Okay. Then we already talked about the type hierarchy in the sense that at the top we had an abstract type number, and then we had real, and we had rational. No, rational was part of real. Sorry. So we had number, we had real, we had complex, and then in real we had integer, we had, so basically that formed the type hierarchy. And as I already mentioned, everything that is not a leaf is going to be an abstract type. Okay, so we can define our own abstract types, and that's just by using type, prepending it with abstract, and the name. So this is just a type definition. Okay. You can subtype an abstract type. So basically, abstract to D point is a subtype of an abstract point. It's itself still abstract. So now we have a hierarchy where we have abstract point at the top, and then it has a child, which is an abstract 2D point. Okay, so this notation here, this less than with the column, is the subtype operator. So basically, that says that in this case, abstract 2D point is in fact a subtype of abstract point. Okay, I could define another subtype, abstract 3D point. Again, it's a subtype of abstract point. So I can create my own hierarchy. All right. So all of these subtypes have, no, let me rephrase that. So any type can have only a single parent type. So you can subtype only from a single type. So that is similar to what you would do in Java, for instance, where you have a single inheritance. That is similar to what you would do in Fortran. Fortran also only supports single inheritance, but that's different from what you can do in C++ or Python, where a class can actually be a subclass of multiple classes. Okay, it's a restriction, but in the context of Julia, one which really doesn't have any impact. So other programming languages get around that. Java, for instance, by having the mechanism of interfaces, Fortran by not really needing it in scientific computing. So basically, since Julia is also for scientific computing, you could argue, okay, single inheritance is going to be enough. But on the other hand, we'll see that Julia defines another way around this restriction using traits, which we are slowly coming to. Okay, so I've got a two-level hierarchy, abstract point with two children, abstract 2D point, abstract 3D point. Okay, so now I can create a concrete subtype. So basically, I create a mutable struct. The name of that mutable struct is point2D, and it's a subtype of the abstract 2D point. And it has an X and a Y coordinate, which are both real numbers. So That is that the x and y can be integer, they can be rational, they can be floating point values. So this is pretty general. Okay. So what you cannot do is subtype from concrete types. So I've already mentioned it at least twice. All the concrete types are leaves in that type hierarchy. All inner nodes in that type hierarchy are abstract types. So that's always true in Julia. That's the typing system, that's how it works. Okay. So now I can start defining functions that operate on points. So, for instance, what is a good idea, so this is recommended, I could directly, suppose I create a point P, which is a 2D point, I could directly access x or y by using p.x, p.y. However, that's not recommended. What is recommended is to create accessor functions. So basically get x that is going to take as an argument p, which is an abstract point, and the function implementation is simply p.x. Okay. Then I can create a function to set the value of x. Remember the convention. Basically, set x is going to modify one of its parameters. So I append an exclamation mark, convention thing. Okay. So this function is going to take two arguments, a point, which is some abstract point, and the value, which is a real. And then it simply assigns that value to p.x. Notice that if I have this notation for functions, I can use it for arbitrarily complicated function bodies by enclosing that in begin and end. Okay, I can do the same thing for y. Okay, and now I make a distinction. So any point has an x coordinate, any point has a y coordinate, but only 3D points will have a z coordinate. So basically, P in this case is going to be an abstract point 3D. Okay, and the rest, of course, is similar, the setter and the getter. Okay, so basically, always define accessor methods. It's considered good practice, and it makes sure that you can actually change implementations very easily, so that decouples the usage of your types from the implementation of your types. That's always good practice, that is good design, so that is why it is recommended. Okay. So now I can create a function, distance. And basically, I'm going to say that these are 2 points which are abstract 2D points. Okay, so that means they do have a get x, a get y, and I can use those in order to compute the distance of these 2 points. I'm just assigning here 2 variables just to make my formula here less convoluted than it would be if I would replicate the get x, get x, get y, get y. That would make my formula difficult to read. So basically, that's why I assign 2 variables. Okay, and then of course I can do the same thing. I define distance again, but now a different method. So the function distance now has 2 methods, one for 2D points and one for 3D points. Okay, so apart from that, it's very similar, only we take into account the z coordinate as well for 3D points. Okay, so basically, this allows me to define specific behavior for specific types in my type hierarchy. And in this case, of course, I can distinguish between 2D points, 3D points. So if I have a concrete type that is a subtype of a 2D point, then basically the distance function, this method defined on 2D points is going to be called. If I have some P1, P2, which are subtypes of an abstract 3D point, then basically it's this method which is going to be called, so the one which takes the Z coordinate into account. Okay. All right, so inheritance is strictly a relation. So basically, an abstract 2D point is an abstract point, and a 2D point, well, a point 2D, basically is an abstract 2D point. So it's always an is-a relationship that is different from what you might be used to in object-oriented languages, where you can have inheritance with different semantics. Usually it is indeed an is-a relation, but it need not be. So basically, the restriction is also in this case that concrete types cannot be subtyped. So that is also a consequence, and also something that makes life annoying. Because suppose I had my 2D point, remember? It was, or a point, don't quite remember how I defined it. Point 2D, okay. Here it is. And so basically now I want a color point. So a color point actually is an abstract point. So it's a special case of an abstract point. It has a point as coordinates, and it has color as a string. Okay. And in this case, I'm also defining a constructor. So color point takes 3 arguments, x, y, and color, and it's going to create a new object based on a point, x, y. That's going to be the value of coordinates and the color. So I have to define my own constructor here, because of course what I would like is to create an object using color, some x coordinate, some y coordinate, and a color. But of course internally this needs to be translated into a point object, and that's exactly what is happening here. So basically the new operator here is going to create a new color point. It takes 2 arguments because there are 2 members. The first member is a point, the second member is a string. Okay, so I use the x and y real values to construct a point. That's the first argument to new. Color is just passed through. Second argument to new, so that is going to be this value here. Okay, so this is called extension by composition. And it's something that you can do in C and C++, sorry, not in C++, not in C, in C++ and in Python, no problem. You can, of course, also do that in Fortran, but for C++ and Python, it's not the only way. So in Julia, it is the only way to extend a concrete type, because you cannot subtype like you would do in those other object-oriented languages. So here you would have to use composition. But that's a little bit annoying, because I've now got this color point, and I would like to get its x and y coordinates. So then that would mean that I would need to write additional methods for the function getX when it applies to a color point. I would have to do something like getX p colored point is p dot chords, or potentially get x of chords, p.chords. And I would have to write that manually for each coordinate, for each attribute, for each member, that one of these types that I used for in the composition actually has. So that's delegation functions. You can do that manually, which is a bit annoying, but actually you can make color point act as a point. So with get and set. So you could re-implement them, or you can delegate, and that's where the lazy module comes in. So that's a pretty standard module in Julia. I think it just comes with Julia. If not, it gets installed automatically, but basically, I think it just comes with it. And then we have this forward here. So basically, the get x is forwarded to color points dot coordinates. So this forward thing here is a macro. So that is going to write code for me. It's actually going to do automatically what I would do by hand. So basically, what I would do if I were to delegate myself is write something like this. So get x, p is a color point. Okay, and that would be get x of p dot coordinates. Okay, so that would be manual delegation. So of course, in this particular case, it's not that much typing, but you can imagine that that gets rather annoying if you have to do that for more sophisticated code. So basically, this delegation using the lazy module and the forward is actually much more convenient. And then you can pick, of course, what you want to forward and what you don't want to forward. But this makes sure that when I create a color point, so say I have P is color point 3, 5, green. Okay, so I could do something like get x of P. So when I call this function now, P is a color point, so it's this method which is going to be executed. Okay, that method is simply going to call get x on P coordinates. So I would get 3 in this case. Okay, so that's delegation. And of course, the lazy module helps there so that you don't have to write that much boilerplate, but still, it's a bit cumbersome in a way. Anyway, that brings us to traits and to something that is often called the holy trait pattern or the holy traits trick. So THTT, basically that means this particular trick. And that depends on traits, and traits are a way to get around single inheritance. So this is something that in other programming languages you would tackle, well, in object-oriented programming languages, you would tackle using multiple inheritance, either using mixins or full-fledged multiple inheritance, but here we are going to do this differently. So traits essentially are sort of a property of types, but they can even be properties of types that are absolutely not related to one another, except that they share that property. And I'll start with the motivating example. So we have a pixel, and of course that pixel has a color. Okay, so I would like to do something like get color of a certain pixel. Right? But paint also has color. So I'd also like to be able to just do get color. So this being colored is a trait, sort of a property of a type. And potentially, as in my rather artificial example, a pixel and paint have nothing to do with one another, except that both can have a color. That's basically the idea. So, okay, how do we deal with that? Well, what we can do is again use a type hierarchy. So we have an abstract type, colored style. Okay. And now we define two structures. One is called is colored, and the other is called is not colored. And both are subtypes of colored style. Okay. So yeah, this is just type definition, nothing more. Okay. What on earth can we do with that? Well, basically, what we can do is say that if we call colored style with any type, then it's going to return is not colored. So basically that means nothing is colored by default. No type is colored by default. Okay, that's a general rule. So of course we need exceptions because, for instance, pixel and paint are colored. Okay, so now we can define some actions. We have a get color, and that takes an object of some type t. So this basically means t here is a type parameter. That's where t comes in. So the type of object determines what is going to happen, and that type is stored in the variable t. So I'm going to apply another getColor method that takes as a first argument the colored style of t. Okay, so this is going to do a type conversion of, well, no, it's going to return a type because that's the function which I defined here. So up to this point, it's always going to return the type is not colored. And that's just a struct here. Okay. And it's going to call getColored on with a second parameter, which is just object. Okay, so basically we have a function getColor, and that's the first method, an arbitrary object, and that's going to call another getColor method, which has two parameters, a type and an object. Well, basically a struct, but okay. So then we create two implementations, two other methods, getColor, where the first argument is not colored, and of course the second argument is object. Well, if an object is not colored, then basically I can't get its color. So basically I give an error where something like, okay, type of object is not colored. Okay. On the other hand, if the object is colored, so that means that getColor gets called with whatever is here as long as it's colored, then the color is going to be returned, and we just have object dot color. Okay. Right. So at this point, of course, any object, no object is colored. So basically, getColor on that object would use type t. Okay. Would determine the colored style of t. So basically, the colored style of any type is a new is not colored struct. So this method getColored with is not colored gets called on with object, and we get an error. Okay, so that's nice, because at this point in time, we have nothing that is colored. So everything we ask the color of is going to give an error, which is good. Right, what do we do with this now? Well, basically, now we can apply the trait. So basically, we can apply the colored thing. So I create a struct pixel, which has a color attribute, which has a color member. Okay, that's one thing. And the other thing is, I create a new method for colored style, which basically takes any type that's a subtype of pixel, and in that case it returns an instance of isColored. Okay, so I create a new pixel with coordinates and a color, and I apply the getColor function. Well, I call the getColor function on pixel. Okay, let's backtrack to the previous slide. GetColor gets called with a pixel object. Oops. So we are here. This is the function method which is called. The object is of some type t, in this case pixel. So t is going to be pixel. Okay. Colored style of pixel is colored. So now we get a method called getColor with a struct isColored and object. So that's this guy here. Okay. And then we do object.color, which we can do because pixel indeed has a color attribute. Okay, so doing that is indeed going to give us blue in this case. All right, so that's pretty cool. If I have an ordinary 2D point and I try to get a color, what is going to happen? Well, okay, now we call this with an object, getColor. Let's again go back here, well, here. So getColor with an object. The type of it is point2D. Okay. So colored style of point2D. It looks for methods. The only method that fits is this guy here with the general type, because point2D is not pixel. Okay, so this is not colored. So basically this method gets called and we get the error. All right, so basically this allows us to assign traits or to apply traits to types. Basically through this holy trait pattern thing. And we can now do the same thing for paint. As I told you, paint and pixels have nothing to do with one another. So basically I create a new type, paint. And the only thing that paint and pixels share is that they have a color property, a trait color. Okay, so I do the exact same thing. I say that colored style of any type derived from paint is colored. Okay, so now there are two types which are colored. One is pixel, the other is paint. And so if I create paint and I ask for the color, I actually get the color. Okay. So this is, yeah, there have even been languages which use this very explicitly, trait-based programming languages. I don't remember a specific example, but basically it is essentially a replacement, if you like, for object-oriented programming, because you can do all the things you can do in object-oriented programming using traits and vice versa. So basically, it has the same functionality. Okay. Why? Why on earth? Why not just use object-oriented programming like any other sane person would do? Well, basically, what the developers of Julia claim is that using traits and using multiple dispatch, which traits actually is, traits is nothing more than exploiting multiple dispatch, that using multiple dispatch will in fact lead to less cohesion between different modules, between different functionalities. And that would make it much more easy to compose functionality. Okay, I read that claim. I did not believe that claim. That claim is false. That claim is false for a very simple reason, and that's a very fundamental conservation law in this universe. That is the conservation of misery. So basically, it's indeed true that if you have, let's say, an object-oriented language and you have very many libraries, that it gets pretty hard to compose them. Okay, that is true. The point is, of course, that if you start out with a new ecosystem which is based on traits, that ecosystem is small. And if one of the things that you are propagating is composability of your ecosystem, then of course everyone pays attention. And that means that for a very small ecosystem, everything is nicely composable and everyone's a winner. Yeah. Until, of course, your ecosystem grows, keeps on growing, and so on. And of course, you lose that property of composability, just like you use it in any object-oriented library kind of thing. Because, yes, indeed, unless you pay very close attention to what you're doing, it's not going to be composable just because you think it's going to be. So, yeah, nice assumption, but no cigar. Yeah. I mean, it's just conservation of misery. What do we expect? All right. But yeah, you can do these kind of things. So basically, note that there is no relationship between types necessary. They just need to share traits in order to have similar functionality, sub-functionality. That's essentially the design thing. So yeah, it's an interesting approach, and it's something that you can also happily do in other programming languages. Typically, what you would call that in other programming languages like Python or like C++, it's just duck typing. In other words, what you look at is properties or behavior of types rather than the type itself. If the type exhibits a certain behavior, it has a trait, and it can act as something. And typically, it's called duck typing because if it quacks like a dog, like a duck, and it swims like a duck, it's most likely going to be a duck because it shares the properties of swimming and quacking with a duck. So that's essentially the idea, and that's exactly what traits are. So in any language you can do duck typing. You are essentially using traits. Here you have to do it with abstract class hierarchies. In C++, you would do this with templates. In Python, you would not bother, and it would work anyway. Basically crashing if you do stupid things, but okay. So essentially, you can do that in many programming languages in slightly different ways, but the concept is always the same. It's very useful to think in terms of traits. It's something that I like to do a lot, also in Python and in C++. So it's quite useful. Whether there is an argument to make it the only means of type extension is a different discussion. But okay, it's what it is. It's the way Julia was actually defined. Okay. you can start breathing again, because this was the most horrible part. So basically from now on, it's a little simpler. Okay, I already mentioned parametric types, and in fact we already encountered parametric types. For instance, rational was a parametric type. Complex could have been a rational parametric type, but isn't, for whatever completely obscure reason. Whatever, I don't care. Anyway, we can also define our own parametric type. So basically, what you can do is say, okay, I have a struct pixel, and I want to be able to specify the concrete type for coordinates and the concrete type for the color later on. So here's coordinate types used, here's the color type used. So I can specify any combination I like. So for instance, I could create a pixel where the coordinates are in unsigned 16. So that would give me coordinates for my pixel between 0 and 2 to the power 16 minus 1. So that's 65,535, which is basically a very big screen. Should work. And the color is in fact a string. Okay. So I explicitly create my coordinates in uint16, and I specify the color blue. And I could create another object, also a pixel, but now the coordinates would in fact be float. And the color would be a uint8, so if you like, a grayscale value. So I can do this, and that gives me different pixels. Now, if pixel is a subtype of point, I didn't specify that, but basically, if I create a getX and a getY for method for the getX and getY functions, and I do that for pixel, then of course I could happily apply the distance function to 2 pixels. Okay, so basically you can do multiple dispatch on abstract parameterized types as well. So all of that works nicely. Okay, so that's all how the whole typing thing fits together, and how you can use that in order to do interesting things with respect to the design of your software. Okay, let's turn to more mundane things like input-output. So textual I/O, you've got the standard streams, std_in to read textual data, std_out, standard error, for output. Okay, so you typically work with file streams, and this is an interesting construct here. So we've got the open function, and that is going to take a name of a file, and it's going to specify a mode. So W, as you can guess, means I'm going to write. This can be R for read, this can be A for append. So those are the modes which you can use. So if my file .txt exists, it's going to be overwritten. If it doesn't exist, it's going to be created. Okay. Now, the grammatical construct is interesting here. So you have open, and then you have do file. Okay. So basically what is happening here is that the file handle, which is created by the open function, is going to be assigned to file. And so in the body of this do end construction, this is do end, I'm going to use file. Where is it? Here, file. And basically what I'm going to do is I'm going to, in my file, write a number of values ranging from 0 to 10 in steps of 0.1. So I'll get 101 values in total, I have to think for a second. It will be 101. Basically, I will get something like, okay, I have the value of x, a space, and then the value of the square root of x. Okay. So basically, this do-and construction might remind Python programmers of context managers. What I would do is with open something as file and then the body. So this is more or less the same thing. So you could view this as a context manager. So that means that as soon as we reach the end of the do block, that the file is automatically going to be closed, which is exactly what a context manager would do in Python. So this is really nice. So this would be another example for reading. So again, we open the file. Now R for read. We have file as the file handle, and we can read each line in file and do something with that line. Okay. So again, this is very similar to Python. Do and plays the role of a context manager. Essentially, a file is the file handle. Each line, well, what I would write in Python is for line in file. I wouldn't have to call each line, but I could use dot read line if memory serves. It's like 50 years ago that I used that for the last time, so I'd have to really think how it is in Python. Okay, so basically, it's a very good idea to use this type of construct because indeed files get closed automatically as soon as this block is finished. Okay, so for formatted I/O, there is a module which is called printf, and that gives you this printf macro, which takes a formatting string and any number of arguments, well, any number, as many as required as the formatting string. And this is essentially the same formatting strings as we would have in C, and are a bit similar to what you would have in Python, but not quite. So this is really the C notation, which is, yeah, it is what it is. Let's put it that way. So basically, this would mean I have a floating point value. Just a second, I need to make sure that my monitor doesn't turn off. I have a floating point value. That's what the f says. And I want to print it with one digit after the decimal dot. Okay. And I have a second floating point value, again the f, with 5 digits after the decimal dot. So basically, I would get 0.1 and then the square root of 0.1, and no, I don't miss a bracket. So note, this is again a macro. So this is going to take these values here, and it's going to create an appropriate function call for that in some way, and you don't have to worry about. So if you're familiar with this type of formula, people who are into C or into what else, into Bash, for instance, the printf function in Bash, it's going to use the same formatting string, then this is very familiar. If not, it's very easy to familiarize yourself with. For instance, I could add another integer before the decimal dot, and then that would act as the width of this field, etc., etc. I would have a d for integers, and so on, so on. It's quite straightforward. Okay, binary I/O, similar. So basically, again, we have we open the file, and we open it for writing, and basically we use the write function. So in this case, we write the consecutive values of the square root of x, and only those, to that file. So this is going to be a file you cannot read. You as a human cannot read, because this is float 64. So basically that would be a sequence of 8-byte values that represent double floating point numbers. And again, in total, there would be 101, one for the square root of 0, another for the square root of 0.1, etc., etc. The last one would be the square root of 10. Okay. Similar for reading, you would read. So this is actually something I do like about the read function in Julia. You just specify the type of what you want to read. So basically, each value I read is going to be a float 64 value. Okay, of course, I need to only read as many values as there are in my file. So basically, this is in a while loop because I don't know how many there are. And I've got the end of file function, EOF end of file, which is false as long as I'm not at the end of the file, which is true as soon as I'm at the end of the file. So basically, as long as I'm not logical operator at the end of the file, I keep on reading. Okay, so quite convenient. Again, of course, you've got this context manager type of thing where the file gets closed at the end of the do block. Okay. There are quite a number for more specialized I/O. So one that's definitely useful is delimited files. So that would be to read, for instance, comma-separated value files, so CSV, or tab-separated files, these kind of things. For output formatting, we already mentioned the printf module. For HDF5 files, there is a module, so basically it's pretty convenient to read and write HDF5 from Julia applications. I'm not sure I have example code for that. I don't think so. Something to be added at some point. Okay. So, as you've already guessed, there is a whole ecosystem out there of modules, and we'll give a few additional examples later on as well. Let's turn to code organization, which is not necessarily the most exciting thing, but it is definitely very useful. So, how do you organize code? Well, there are many ways, well, not many ways to do it. Let's rephrase that. Any programming language has ways to do that. So, for instance, Fortran does have modules. These are separate files, typically, in which you have a syntactic thing, which is a module, and which is a collection of functions, of type definitions, of constant declarations, and so on, which you can then import into your code with the use statement in Fortran. In Python, you have something similar. Basically, you have modules. A module is essentially just a file. There is no module declaration thing, but it holds a collection, again, of functions, of class definitions, of whatever, and you can import that using the import statement and so on. So in C++, you would use header files. So each and every programming language has a way to modularize code, and of course, so has Julia. So this would be a model definition, and it also defines a namespace. So essentially, it encapsulates functions so that functions in different modules can still have the same name. Okay, so my model definition is in a file by itself, typically with as name the name of the module, .jl. I didn't mention it, but you probably guessed .jl is the extension for Julia files. Okay, the name of my module is my functions, and it contains function definitions. As you can see, there is a function fact, there is a function gcd, and I've export fact, but not gcd. Okay, so basically, how do I use that? Well, I can do it using my functions. Okay, And then I can simply print the fact of 3, for instance. Okay. This happens, this works, because I explicitly exported fact. So using my functions will bring fact into the namespace of this file, in this case, myscript.julia. However, GCD was not exported. I can still use it, but then I have to specify the namespace qualifier. So basically the name of the module dot the name of the function. Okay. So if I want to be selective, if I don't want to use everything that's exported by the module, I can restrict that. So basically I can say, okay, using my functions, but I only want to import fact into my namespace. So this would still work, but any other exported function is not going to be in my namespace here. So this would be a little bit similar to an import, well, to a from something import star in Python, which is not necessarily a very good idea. So this would be the equivalent of from my functions import fact. Okay, so in general, this is good practice because it doesn't pollute your namespace. You have no idea which functions are exported by a module. So essentially, you are polluting your namespace with stuff you don't know about. So that may bring in additional methods for functions you defined, because they happen to have the same name, and hence they would be added as methods to a function you define. So that's not necessarily interesting. Okay, so basically, if you want to do that explicitly, you want to add methods to a fact function, you can do that by import rather than using my function fact. Then you add it as a namespace explicitly. Okay. You can use aliases as well. So basically, you can give it a different name. So it's very similar as you would do in Python. Okay. So basically, pretty straightforward. I don't really think there are many surprises here. Of course, there's nothing that says that you need to export anything at all. So basically, you can just say, okay, if someone wants to use stuff, okay, just use the namespace qualifier. Okay. Then packages. So essentially, you can create a package for this GCD module, and this you can actually do from the interpreter. So basically, you can get into the package manager by pressing a closing thing. So let me show you, because that is better. Okay, let me start new terminal, because I don't want to do this in this directory, because then I need to clean it up, and still I have mine open, so that's not so very convenient. So let's go to my TMP directory. Okay, so what I can do is I start Julia. I go into the package manager. So I typed closing square bracket, and now I can generate, for instance, GCD. Okay, so it has done a number of things. Basically, it has created a new directory, and in that there is a project toml file, and there's a source directory. So I go out of this package manager by Control-C. Okay, I'm back in the Julia. interpreter, but I'm just going to exit that as well. Okay, so I go to the GCD directory. As you can see there is this project TOML file, and that contains a number of things. So meta information about this package. So as you can see, there is a default version specified, 0.10. The name is specified. The author is specified. No idea where I got that from. It's nice, it's correct, but I don't remember offhand where it gets this from. So probably it will ask the first time it does this or something like that. I don't quite remember. Anyway, what is also here is this UUID. So that's a universal unique identifier, and basically it's a hash that allows people to identify this package. So what it would further contain down the road is dependencies and so on. So all of this is specified in this TOML file. Okay, so in source directory there is a very rudimentary module. So the module is declared essentially, and yeah, there is a very stupid hello world function defined, which is called greet, and which will just print hello world. So not particularly exciting, but basically that is what you get by default. And then of course you can start working on this. Okay, so yeah, that's what you get. That's the TOML file. So basically one of the things you need to do is that if you want to use this project, you would have to actually have to make sure that the parent directory, so in my case that would be this guy here, is in fact in an environment variable, Julia load path. We can see which value it has. It shouldn't have any. I don't have any environment variable defined with Julia, so I could do Julia load path. Whoops, good capitalization, all right. $PWD. Okay, and now Julia will actually find this GCD module if I require it. Okay, so that's the way to create packages, and of course you can create as many packages as you would like. Okay. If you develop your own libraries, then basically it's a good idea to add documentation, and that is very similar essentially to what you would do in Python, except that your documentation string goes before your function definition rather than in your function definition. So basically all of this between the triple quotes thing is your documentation, and that applies to the function mygcd, which is here. Okay, so basically you will see that this looks like and actually is marked down. So basically this will be formatted nicely when you display it. So that's quite convenient. The usual stuff applies. So basically this would be a level 1 header. Arguments would be a level 1 header. This would be a list, I think. I think there's a dash here. Sorry, I can't read my own file anymore. I think this is a dash. So basically, it's a bulleted list. Here I have a code fragment. So basically, triple backquote and triple backquote and so on. Okay. So yeah, you can make this quite extensive. And then, for instance, in a notebook, I could ask for help on my GCD, and then I would get this nicely formatted as marked down in my notebook. Okay. So yeah, this is a convenient way of doing things. similar to what you would do in Python, with some syntactic differences in the sense that the string goes outside rather than inside. Note that that is another similarity with Python, which I didn't mention when I was talking about strings. Multi-line strings can be quoted by triple double quotes. So all of this is one very long string. And that's exactly the same as you would do in Python. Okay. So, of course, programming language is nice, but it's pretty useless unless you have a strong ecosystem. And of course, Julia is a reasonably young language, but it already has quite an interesting ecosystem, especially, of course, with respect to scientific computing, what it was designed for, basically. So, yeah. So there is a standard library. A few things that are useful. So PKG, that's your package and environment handling. So PKG also allows you to create an environment tailored to a project. So with the dependencies, the Julia modules and packages which you require for that module installed in that environment and nowhere else. So that's where PKG comes in. Printf we already mentioned twice. Limited files we mentioned. So basically, there is also iterations, and those are lazy iterators essentially. There are quite a number of third-party libraries. One which I particularly like is benchmark tools. So that's very similar to the magic timeit in Python notebooks. So basically it will also do statistics. Do I have an example of that? That would be cool. Let me see. I should have, but the question is where. Performance sounds like a likely place to find something like that. Let's see. Yeah, so here I'm using benchmark tools, so that's good. That's indeed what I wanted to see. So basically, this would be the example of benchmark tool, the output of benchmark tools. So basically, it's a bit more informative than Python's timeit in the sense that it also gives you this histogram of times. So basically, you see that independent runs are done. It should list how many. In this case, 1012 samples. Okay. And basically this histogram represents the execution time distribution. You also get statistical information like the mean value, but also the median. And this, of course, is quite useful because the median, as you know, is much more robust with respect to outliers. And as you can see, there is an outlier here which took a very long time. This, of course, can, for instance, be the first time that, although unlikely because there are two of them, so probably this is just fluctuation. Basically, it will determine quite a number of things. This is also a useful one, GC. This is the garbage collection. So basically, that is dealing with cleaning up stuff that was allocated in memory. And so basically, that is also something that happens, and that essentially takes some time. So this is also good to know that information is actually given. Okay, so it's a bit richer than timeit, but it's essentially the same purpose. So this, of course, is micro-benchmarking. You are evaluating one particular expression, Note again, this is a macro. So basically it's going to generate code in order to run some columns called on A multiple times. So this is micro benchmarking, and of course micro benchmarking is useful, but yeah, it's not profiling. So it's a useful tool, but okay. Then there's struct arrays, and that's an interesting one because suppose that I have something that is conceptually a point, or let's say that is conceptually a particle. And the particle has a position, it has a velocity, and it has a mass, for instance. Okay, so basically for each particle, I need to keep track of 7 values in total, 3 spatial coordinates, 3 components of the velocity, and the mass. Okay, so now I want to consider a system of many particles, and I have 2 choices to implement this. I could create an array that contains structs where each struct represents an individual particle. That's one approach. The other approach is that I say, no, I'm not going to do that. I'm going to create a struct that contains 7 arrays. The first array is going to contain the x coordinates of all the particles. The second array is going to contain the y coordinate of all the particles, and the last array, mass, is going to contain the mass of all the particles. And then I can get specific information about the particle just by specifying the index, the particle number if you want, into that array, and I get the x, y, etc., properties of that particular particle. So those 2 approaches are similar, and you might think, well, okay, actually it seems a bit more natural to think of an array of structures rather than a structure of arrays. Okay. Unfortunately, in many situations, the structure of arrays is faster than the array of structures. Now, of course, converting from structure of arrays to an array of structures, or vice versa, is just a very simple mechanical process. The only thing you need to do is to say, well, okay, I've got n particles total. So if I have an array of structs, the only thing I need to do is to create a new to define a new struct which has arrays as elements, as many as the struct has members, and I know the size of those arrays because I know the number of particles. Easy. And if I want a particle, it's accessing individual components versus and so on. So I can do something similar as forward. So basically I can automatically generate or convert between the 2. And that's exactly what struct arrays allows you to do. And that's pretty nice because typically in other programming languages, you start rewriting your code. In Julia, you can just use struct arrays. Maybe there are some template libraries in C++. I would actually have to check, because it should not be too hard in C++ and even in Python to do this. So perhaps there are similar things. But it's nice to know that it exists. It's a good example. There are quite a number of plotting libraries. I have to update Getfly because that's old and not exactly your go-to library anymore. And of course, by now I forgot the name of the modern alternative to Getfly. So I need to check that. Don't remember. There was a way nicer alternative, but of course I forgot. So essentially, if you want pandas, like behavior for data science, then there is a data frame package which has similar functionality to pandas. Is it really an alternative? honestly, I didn't look into the details because if I really want to do data science, I'm probably going to do it in Python anyway, because the ecosystem related to that is much larger in Python than it is in Julia. So I didn't look into it. But if you say, okay, I use pretty basic functionality of data frames, nothing too fancy, and it should go pretty fast, then you might want to have a look at data frames in Julia. There is also a module which is very close to the ArcParse module in the Python standard library. So that's to handle command line arguments. For C++, you can do that in Boost, you can do that in CLI 11. There are similar libraries. So that's a useful one if you have scripts which you run from the command line and you need to deal with command line arguments. ArcParse is going to be your friend. Okay, as you can see, we are somewhat at the end of this training. So I'll draw some conclusions and then point you to some things which might be interesting to have a look at, which I didn't have time to go into. So is Julia good? Is it bad? Is it ugly? I think you understand that some things I really like, some things I think are not such a good idea, and some things are downright ugly, but that is mostly a matter of opinion. It's a matter of taste. So it's up to you to determine what's good, bad, and ugly about any programming language, including Julia. So basically, it's totally up to you. A few books which are of interest, or references which are of interest, the Julia documentation, obviously, which is quite good. And there's also a book, Hands-on Design Patterns and Best Practices with Julia, which is also worth looking into. It's getting a little bit dated. It's now 6 years old, but okay, it's still kind of interesting. So there is someone who actually created the Google Colab template for that. I didn't test whether that still works, but yeah, you can do that. I'd say normally run it on your own machine with a notebook or directly at command line. So yeah, that's easier. Okay, let me first ask whether there are any questions and then point you to some stuff which might be interesting as well. Are there any questions at this point? Things that are unclear? Not really. Okay, so things that you might want to have a look at. Question. What do you think is the ideal use case for Julia? Well, essentially, I would say the most ideal use case is you have something in MATLAB, it's too slow, write it in Julia. There are also projects which are started in Julia. So actually anything you want to do in the domain of scientific computing, and then typically I mean numerical computing, so simulations, that kind of thing. Julia is a very good candidate to do that. That's beyond discussion. There are a few drawbacks, let's be honest. First, there are not that many Julia programmers. So that basically means that if you are a PI and you make the decision, okay, we are going to develop to do long-term software development in Julia, it means that if you get a new PhD candidate, that person will have to familiarize him or herself with Julia, which is a bit more annoying than for more mainstream programming languages, because there is less training material and very few trainings about Julia anyway. So yeah, that's a consideration which you do have to take into account. The ecosystem is large, but of course it's much smaller than other programming languages which have been established for decades, like C++, like Fortran. So there is a lot for Julia, but yeah, not as much as you might hope for. Of course, you can always bridge between programming languages by doing foreign function calls and so on. But yeah, that adds to the complexity, so that may or may not be the way you want to go. So that would be a little bit my take on that. That sort of answers your question. Yeah, okay. So other things which might be worth looking at. So out of the box, Julia can do some parallel programming. So basically, there is distributed programming as well as multi-threaded programming. So basically, there are a few examples here. So this one is using distributed, which essentially means that it is, at least in theory, you should be able to run it on multiple compute nodes, so a little bit like MPI, while the implementation of Pi is, I think, thread-based. We can have a look. PI threads. I have it both with distributed and with threads. That's convenient, and you can compare. So basically, this would be the code. And where's my compute Pi? Okay. So here, basically, I'm multi-threading. So this is like, say, an OpenMP, but it's done with macros in this case. So basically, the code which is here, this for loop, is rewritten in such a way that multiple threads will do part of the iterations. So that's how that would work. The ecosystem for scientific computing, yeah. Well, with respect to HPC, there is a lot, but of course there is more for Python. So it depends a little bit on what you actually need. So if I were to start on a new project and I'd consider using Julia, the first thing I do, of course, is to check the relevant packages in the ecosystem, whether they exist. I'll do the same exercise for Python, check whether they exist, what exists, how they relate to one another, in the sense that is, for instance, the Python implementation more convenient? Is the Python implementation performant, etc., etc.? So that's something that you need to do anyway, and you would have to kind of do that on a project-by-project basis. So, for instance, what I would be very unlikely to do is, for instance, natural language processing in Julia, because I know that the Python ecosystem is really, really, really mature. So the probability that you find something equivalent in Julia is low. So that would be my first guess. Of course, I would have to check, and maybe I would be proven wrong, although I think in this case my intuition will be good. With respect to, for instance, machine learning, there are Julia packages to do machine learning, but yeah, can they really stack up to PyTorch or to TensorFlow? Unlikely. So those would be two areas where I would be very likely to pick Python over Julia. On the other hand, if I were to write, for instance, a new solver implement a new solver for partial differential equations, then Julia would be an excellent candidate. I would not rely that much on the ecosystem, so yeah. Okay, so parallel is definitely something to look at. Let's see, the ecosystem, nothing too exciting there. I really have to replace Gadfly because it's really too old. Okay, no, I think that's more or less it. The notebooks typically illustrate, so Julia Features broadly illustrates whatever I said in the presentation. Specialization here illustrates the usage of traits. So that's an implementation of what you find in the slides with respect to traits. Okay, semantics. Yeah, this is a bit of basically some experiments to see what happens if you try to push things a little bit. Okay. Yeah, performance-wise. Okay. So theoretically, Julia can have excellent performance because it gets compiled to machine code, and depending on the quality of your compiler, it can really do an excellent job. I would have to verify how Julia works at the moment. I think it compiles, it has its abstract syntax tree, and then immediately converts that to machine code. So then it depends on how well the optimization works. Of course, Fortran compilers have decades of history of being tuned for optimization and doing very aggressive optimizations, resulting in very fast code. So Julia is fairly young. It probably learned a lot from Fortran compilers. So it's probably not as good in all circumstances, but in ideal circumstances, it should be equivalent. But in practice, I think it's still lagging behind a bit with respect to performance. But you'd really have to do an apples by apples comparison. So a very well written Fortran code, a very well written Julia code, which does the same thing, and then compare. And those benchmarks are always very dangerous because, yeah, they need to be done by someone who knows both languages in and out to get a really good comparison. So it's a bit tricky, but you can get excellent performance with Julia, that's for sure. And of course, similar for C and C++, it's the same thing. If you write efficient C++, it's going to be very performant, comparable to Fortran. If you write crappy C++, it's going to be slow. So yeah, it depends. Here also, you will have to tune your code a little bit for performance, choosing types very, very carefully, things like that. Other questions? Okay. If not, I suggest we conclude here. So thanks for attending, and yeah, maybe see you in some other training related to HPC, to scientific computing, or whatever. So enjoy the rest of your day.